The observable universe, the region of space from which light has had time to reach us since the Big Bang, extends approximately 46.5 billion light-years in all directions from Earth. This distance, called the comoving distance or proper distance, accounts for the expansion of space that occurred while light travelled toward us. The observable universe's diameter is therefore about 93 billion light-years, encompassing everything we can possibly observe with telescopes, regardless of technological advancement. Beyond this boundary lies the cosmic horizon regions of space, whose light hasn't reached us yet and may never reach us due to accelerating expansion. The 46.5 billion light-year radius seems paradoxical at first. The universe is 13.797 billion years old, according to measurements from the Planck satellite published in 2018. If light travels at 299,792 kilometers per second, 1 light-year per year, we might expect the observable universe to extend only 13.8 billion light-years. Light from the most distant objects has been travelling for 13.8 billion years, so how can those objects now be 46.5 billion light-years away? The resolution: space itself expanded while light travelled. Objects that emitted light 13.8 billion years ago were much closer then, only about 42 million light-years away. But cosmic expansion carried them to 46.5 billion light-years distance during the 13.8 billion years their light took to reach us. This expansion is described by general relativity through the Friedmann equations, derived by Alexander Friedmann in 1922 and independently by Georges Lemaitre in 1927. These equations govern how the scale factor, a measure of the universe's size, changes with time. As the scale factor increases, distances between galaxies increase proportionally. A galaxy that was 1 million light-years away when the universe was half its current size is now 2 million light-years away. The expansion affects all distances uniformly. Space itself stretches rather than galaxies moving through static space. The comoving distance to the cosmic horizon can be calculated by integrating the speed of light divided by the scale factor from the Big Bang to the present. This integral accounts for how light traversed a universe that was continuously expanding. In the early universe dominated by radiation and then matter, expansion slowed over time, deceleration caused by gravitational attraction of matter. Light travelled farther relative to the scale factor than it would in a static universe. More recently, dark energy has accelerated expansion, but this acceleration is recent enough that it doesn't dramatically affect the total comoving distance to the horizon. The observable universe contains approximately 2 trillion galaxies based on deep field observations from the Hubble Space Telescope. The 2016 estimate by Christopher Consolis and colleagues at the University of Nottingham analysed galaxy number counts at different distances and extrapolated to regions too distant or faint to observe directly. Each galaxy contains roughly 100 million to 1 trillion stars on average, suggesting the observable universe contains roughly 10 to the 24th power stars, a trillion stars. The total number of particles, mostly photons from the cosmic microwave background, is approximately 10 to the 90th power. The particle horizon, another term for the observable universe's boundary, differs from the event horizon. The particle horizon represents the farthest distance from which light could have reached us by now. The event horizon represents the farthest distance we could theoretically reach by sending a signal today at light speed, given accelerating expansion. Due to acceleration driven by dark energy, the event horizon is closer than the particle horizon, roughly 16 billion light-years in comoving distance. Galaxies beyond the event horizon are causally disconnected from us. We cannot affect them, and their current state cannot affect us, though we still receive ancient light they emitted billions of years ago. The observable universe is finite but unbounded in a specific sense. It's finite, containing a definite volume and mass, but unbounded because you never reach an edge. If the universe has flat or hyperbolic geometry, you could travel forever in a straight line without encountering a boundary, always finding more space. If the universe has spherical geometry, like the surface of a sphere but in 3 dimensions, traveling far enough would return you to your starting point, analogous to circumnavigating Earth. Current measurements favor flat geometry, suggesting the universe extends far beyond the observable region, possibly infinitely. Measuring the observable universe's size requires understanding cosmic distances. Astronomers use a distance ladder, a series of overlapping measurement techniques extending to greater distances. Parallax works to a few hundred light-years. Cepheid variable stars extend to 100 million light-years. Type Ia supernovae reach billions of light-years. For the most distant objects, redshift provides distance information. Redshift Z measures how much light's wavelength stretched due to expansion. The cosmic microwave background has redshift Z equals 1090, meaning wavelengths expanded by a factor of 1091 since emission. The relationship between redshift and distance depends on the universe's expansion history, encoded in the Hubble parameter's evolution. The Hubble parameter h equals the rate of change of the scale factor divided by the scale factor, essentially the fractional expansion rate. At present, h0 equals approximately 67 to 73 km per second per megaparsec. There's a discrepancy between measurement methods that remains unresolved. Using h0 and knowing how the universe's composition changed over time, radiation dominated, then matter dominated, now dark energy dominated cosmologists calculate the relationship between redshift and comoving distance. For redshift Z equals 1, corresponding to light emitted 7.7 billion years ago, the comoving distance is about 10.3 billion light-years. For Z equals 10, corresponding to 13.2 billion years ago, when the universe was only 480 million years old, the comoving distance is about 32 billion light-years. For the cosmic microwave background at Z equals 1090, emitted 380,000 years after the Big Bang, the comoving distance is 46.5 billion light-years. These distances are larger than light travel times because expansion stretched space during light's journey toward us. The observable universe's edge is not a physical boundary, but an observational limit. Light from beyond hasn't reached us yet. As time passes, the particle horizon expands, we see farther. But accelerating expansion complicates this. In a decelerating universe, the horizon expands faster than the universe, eventually encompassing everything. In an accelerating universe driven by cosmological constant, the horizon's expansion slows. Distant galaxies recede faster than light due to space expansion. Light from galaxies beyond the event horizon, emitted today, will never reach us. Expansion carries them away faster than light approaches. The 93 billion light-year observable universe represents our cosmic address, the region causally connected to us. Everything we observe, every photon detected, every particle that could have influenced Earth, originated within this volume. Beyond lies the unknown space that exists but remains forever hidden unless we develop faster-than-light travel or wormholes, both implausible given known physics. The observable universe is all we can ever hope to observe through electromagnetic radiation, gravitational waves, or neutrinos. It's our cosmic horizon, the boundary between the known and unknowable, the 13.8 billion year age that defines our cosmic horizon. The universe's age is 13.79 7 billion years, with uncertainty of plus or minus 0.023. Billion years about 23 million years, according to the Planck satellite's final data release published in 2018. This measurement comes from analyzing the cosmic microwave background's temperature fluctuations, which encode information about the universe's composition, geometry, and expansion history. The age calculation assumes the lambda CDM model, the standard cosmological model featuring a cosmological constant lambda, representing dark energy and cold dark matter, abbreviated CDM. This model successfully explains observations from the cosmic microwave background, supernovae, galaxy surveys, and the abundance of chemical elements. The Wilkinson Microwave Anisotropy Probe, or WMAP, which operated from 2001 to 2010, provided earlier measurements of the universe's age. WMAP's 9-year data release in 2012 gave 13.772 billion years, with uncertainty 0.059 billion years. The agreement between WMAP and Planck, both measuring the same phenomena with independent instruments, validates the measurements. The Planck satellite, launched by the European Space Agency in May 2009 and operated until October 2013, had better angular resolution and sensitivity than WMAP, reducing uncertainties and refining the age estimate. Multiple independent methods confirm this age. Globular clusters, spherical collections of hundreds of thousands to millions of ancient stars, contain the oldest stars in the Milky Way. By measuring these stars' luminosities, temperatures, and chemical compositions, astronomers estimate their ages from stellar evolution models. The oldest globular cluster stars have ages around 13.2 billion years, with uncertainties around 1 billion years. These stars formed very early in the universe's history, within the first few 100 million years, so their ages provide a lower bound on the universe's age. The cosmic age of 13.8 billion years comfortably exceeds the oldest stellar ages. White dwarf cooling provides another age measurement. White dwarf stellar remnants left after sun-like stars exhaust their nuclear fuel cool slowly over billions of years, gradually dimming and reddening. The coolest, faintest white dwarfs are the oldest. Surveys measuring white dwarf temperatures and luminosities reveal a cutoff, an absence of white dwarfs cooler than a certain temperature. This cutoff reflects the age of the oldest white dwarfs, which haven't had time to cool further. Observations give white dwarf ages consistent with 12 to 13 billion years for the oldest, again compatible with 13.8 billion year cosmic age. The age calculation from the cosmic microwave background depends on measuring several cosmological parameters: the Hubble constant, the densities of matter and dark energy, the geometry of space, and smaller contributions from radiation and neutrinos. The cosmic microwave background's temperature fluctuations, hot and cold spots varying by about 100 microkelvins, encode these parameters through their statistical properties. The angular size of typical fluctuations depends on the sound horizon at recombination, how far sound waves travelled in the early plasma before atoms formed. This distance, projected onto the sky, depends on the universe's geometry and expansion history. The Planck satellite measured the cosmic microwave background's temperature as 2.7255 Kelvin with uncertainty 0.0006 Kelvin. This temperature, combined with the fluctuation pattern, determines the universe's thermal history. The cosmic microwave background formed when the universe was 380,000 years old at temperature 3000 Kelvin. The universe has since expanded by a factor of 1091, cooling the radiation from 3000 Kelvin to 7,255 Kelvin. The expansion factor's time evolution determines the age, how long it took to expand by factor 1091, depends on the expansion rate history, which depends on the densities of various components. The universe's expansion rate changed dramatically over its history. In the first 50,000 years, radiation dominated photons and relativistic particles contributed most energy density. Radiation dilutes faster than matter. When space expands, energy density scales as 1 over scale factor to the 4th power for radiation, 1 over scale factor cubed for matter. Around 50,000 years after the Big Bang, matter density overtook radiation density, beginning the matter-dominated era. Matter dominated until about 9 billion years ago, when dark energy density, which doesn't dilute with expansion, overtook matter density. Since then, dark energy has dominated, causing accelerated expansion. The age formula integrates the inverse Hubble parameter from the Big Bang to present. The Hubble parameter h equals the rate of change of the scale factor divided by the scale factor. In general relativity, h squared equals 8 pi times Newton's gravitational constant divided by 3 times the total energy density. The energy density includes contributions from matter, radiation, dark energy, and curvature. As these contributions evolve with the scale factor, the Hubble parameter changes, and integrating 1 over h from scale factor 0 to 1 gives the universe's age. Early in cosmic history, the universe expanded rapidly due to high energy density. In the radiation-dominated era, the scale factor increased as the square root of time, meaning the universe doubled in size every time interval proportional to itself. In the matter-dominated era, the scale factor increased as time to the 2/3 power expansion slowed as gravitational attraction between matter decelerated expansion. Recently, dark energy dominance has caused exponential expansion. The scale factor grows exponentially with time, accelerating expansion. The age is the integral over these different epochs, each contributing differently to the total. Uncertainties in the age measurement come primarily from uncertainties in the Hubble constant. The Planck satellite infers h0 equals 67.4 kilometers per second per megaparsec from cosmic microwave background analysis. But local measurements using Cepheid variables and supernovae, led by Adam Rees at Johns Hopkins University, give h0 equals 73 kilometers per second per megaparsec as of 2022. This 8% discrepancy, the Hubble tension, implies either systematic errors in measurements or new physics beyond the standard model. Higher H0 means faster expansion and younger age, about 12.8 billion years instead of 13.8 billion years. The Hubble tension remains unresolved despite extensive investigation. Multiple teams have checked for systematic errors in both cosmic microwave background and local measurements, finding none large enough to explain the discrepancy. Proposed resolutions include early dark energy, a component that dominated briefly in the early universe, increasing early expansion rates, or varying fundamental constants that change how expansion evolves. Some propose that the universe's expansion rate varies with direction to a dipole in the Hubble constant, though this would violate cosmological principle of isotropy. The universe's age matters for interpreting observations. Stars, galaxies, and structures take time to form. The oldest stars formed within the first few 100 million years, requiring at least that much time. The oldest galaxies observed by the James Webb Space Telescope at redshift Z greater than 10 existed when the universe was only 400 to 500 million years old. Understanding galaxy formation timelines requires knowing cosmic age precisely. The age also determines the horizon size, how far light could have travelled, defining the observable universe's extent. If future measurements definitively establish a younger age, say 12.8 billion years, from a 73 km per second per megaparsec, Hubble constant cosmologists would need to reconcile this with stellar ages. Stars in globular clusters can't be older than the universe itself. Either stellar age estimates require revision possible if stellar evolution models have systematic errors or the discrepancy indicates new physics. The Hubble tension might force modifications to lambda CDM model, adding new components or revising assumptions about homogeneity and isotropy. The cosmic microwave background from 380,000 years after Big Bang. The cosmic microwave background, or CMB, is radiation left over from the hot, dense, early universe. This radiation fills all of space, arriving from every direction with nearly uniform temperature, 2.7255 Kelvin, only 2.7 degrees above absolute zero. The CMB formed 380,000 years after the Big Bang at an event called recombination, when electrons and protons combine to form neutral hydrogen atoms. Before recombination, the universe was an opaque plasma photons, constantly scattered off free electrons, making the universe foggy. After recombination, photons streamed freely through transparent space, creating the CMB we observe today as a snapshot of the universe at 380,000 years old. Recombination occurred when the universe cooled to approximately 3000 Kelvin. At higher temperatures, thermal photons had enough energy to ionize hydrogen atoms, breaking them into protons and electrons. As expansion cooled the universe below 3000 Kelvin, photons lacked energy to ionize hydrogen. Electrons and protons combined and stayed combined. This transition happened rapidly over tens of thousands of years around the 380,000 year mark. The transition's name recombination is technically a misnomer because electrons and protons hadn't combined before. The first combination should be simply combination, but the term recombination persists historically. The CMB's temperature of 3000 Kelvin at recombination has since redshifted to 2.7255 Kelvin due to cosmic expansion. Light's wavelength stretches as space expands redshift. The temperature of blackbody radiation scales inversely with wavelength, so temperature decreases proportionally with the scale factor. The ratio 3000 divided by 2.7255 equals approximately 1091, meaning the universe has expanded by a factor of 1091 since recombination. This corresponds to redshift Z equals 1090 wavelengths have stretched by factor 1 plus Z equals 1091. Arno Penzias and Robert Wilson discovered the cosmic microwave background accidentally in 1964 while working at Bell Telephone Laboratories in New Jersey. They were calibrating a radio antenna designed for satellite communications when they detected persistent noise at microwave frequencies coming equally from all directions. Initial thoughts blamed the noise on pigeon droppings inside the antenna, but cleaning didn't eliminate it. Nearby at Princeton University, Robert Dick, Jim Peebles, and colleagues had predicted that residual radiation from the Big Bang should be detectable as microwave background with temperature around 5 Kelvin. When Penzias and Wilson learned of this prediction, they realized their noise was cosmic. Penzias and Wilson published their discovery in 1965, reporting excess antenna temperature at 4080 MHz of 3.5 Kelvin. Dick's team published a companion paper interpreting this as primordial radiation. Subsequent observations at multiple frequencies confirmed the radiation followed a blackbody spectrum, the characteristic spectrum of thermal radiation determined purely by temperature. In 1978, Penzias and Wilson received the Nobel Prize in Physics for their discovery, which provided crucial evidence for the Big Bang theory over competing models like steady-state cosmology that predicted no such background radiation. The Cosmic Background Explorer satellite, or COBE, launched by NASA in November 1989, made the first precise full-sky map of the CMB. COBE carried 3 instruments. FIRAS measured the CMB spectrum, confirming it perfectly matched a blackbody at 2.735 Kelvin. DMR mapped temperature variations across the sky. And DERB measured infrared emission from dust. COBE's DMR instrument detected temperature fluctuations, anisotropies of about 100 microkelvins on angular scales of 7 degrees. These tiny fluctuations represented density variations in the early universe that seeded structure formation. John Mather and George Smoot, COBE's principal investigators, received the 2006 Nobel Prize for this work. COBE's angular resolution of 7 degrees was coarse, unable to resolve finer details in the CMB fluctuation pattern. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in June 2001, improved angular resolution to 0.2 degrees, 35 times sharper than COBE. WMAP operated from the second Lagrange point, or L2, a gravitationally stable location 1.5 million kilometers from Earth, opposite the Sunday. From this vantage, WMAP mapped the entire sky over 9 years, measuring temperature variations with precision around 20 microkelvins. WMAP's detailed maps revealed the CMB's fluctuation spectrum, the statistical distribution of hot and cold spots at different angular scales. The fluctuation spectrum shows peaks preferred angular scales where fluctuations are stronger. The first peak occurs at angular scale approximately 1 degree, corresponding to the sound horizon at recombination. The distant sound waves travelled in the 380,000 years before recombination. This scale, about 490,000 light-years at recombination, now appears as 1 degree angle on the sky, given the universe's geometry and expansion history. The peak's location directly measures the universe's curvature. A flat universe produces peaks at specific angles. Positive curvature closed, spherical geometry shifts peaks to larger angles. Negative curvature open hyperbolic geometry shifts peaks to smaller angles. WMAP's measurements showed peaks at locations corresponding to flat geometry within 1%. The Planck satellite, launched by ESA in May 2009, provided the most detailed CMB measurements to date. Planck operated at L2 like WMAP, but with better sensitivity and angular resolution, around 5 arc minutes, 2.5 times better than WMAP. Planck observed at 9 frequency bands from 30 to 857 GHz, allowing separation of CMB from foreground emissions like dust and synchrotron radiation. Planck operated until October 2013, producing maps and scientific data through 2018. The Planck 2018 data release refined cosmological parameters to unprecedented precision, measuring the universe's age to 0.2% and curvature to 0.1%. The CMB's temperature fluctuations encode the universe's initial conditions, the density variations that grew through gravitational instability into galaxies, clusters, and the cosmic web. Regions slightly denser than average at recombination appear as cold spots in the CMB photons. Climbing out of gravitational wells lose energy, getting redshifted. Regions slightly less dense appear as hot spots. The amplitude and pattern of fluctuations depend on the universe's composition, how much dark matter, baryonic matter, dark energy, and radiation existed. Matching observed patterns to theoretical predictions constrains these components' abundances. Polarization of CMB photons provides additional information. Scattering of photons off electrons at recombination creates linear polarization patterns. These patterns divide into E modes curl-free patterns, like electrostatic fields, and B modes curl patterns like magnetic fields. E modes are generated by scalar density fluctuations, the same fluctuations creating temperature variations. B modes can be generated by gravitational waves from inflation, ripples in space-time produced during the inflationary epoch. Detecting primordial B modes would directly confirm inflation, but no definitive detection exists yet. The BICEP 2 experiment claimed detection in 2014, but subsequent analysis showed the signal came from galactic dust. The CMB surface, the last scattering surface, is not a physical surface, but a spherical shell centered on us at comoving distance 46.5 billion light-years. Every observer in the universe sees their own last scattering surface centered on themselves at the same comoving distance. The surface represents the farthest we can see with photons. Before recombination, the universe was opaque. We cannot see farther using electromagnetic radiation. Neutrinos decouple earlier, creating a cosmic neutrino background from 1 second after the Big Bang. Gravitational waves decouple even earlier, potentially providing a window to the first 10 to the minus 36 seconds. But the CMB remains our clearest view of the early universe's state. The CMB's near-perfect isotropy and Planck's spectrum pose challenges explaining without inflation. The isotropy problem. Regions of sky separated by more than 2 degrees were never in causal contact before recombination. According to non-inflationary Big Bang models, light hadn't had time to travel between them. Yet the CMB has the same temperature everywhere, to 1 part in 100,000. How did these causally disconnected regions reach thermal equilibrium? Inflation solves this. Before inflation, the universe was small enough for all regions to thermalize. Then inflation expanded space faster than light, stretching causally connected regions beyond each other's horizons while preserving uniform temperature. The inflation that stretched space faster than light. Cosmic inflation is a period of extremely rapid, exponential expansion that occurred in the universe's first fraction of a second. Proposed by Alan Guth in 1980 while at Stanford Linear Accelerator Center, inflation solves several problems in standard Big Bang cosmology: the flatness problem, the horizon problem, and the magnetic monopole problem. During inflation, the universe expanded by a factor between e to the 60th power and e to the 100th power, between 10 to the 26th and 10 to the 43rd power, in approximately 10 to the minus 36 to 10 to the minus 32nd seconds. This extreme expansion stretched space faster than light, not violating relativity, because space itself expanded, not objects moving through space. The flatness problem. The universe's geometry is extremely close to flat. The total density equals the critical density to within 0.1%. But flatness is unstable in standard cosmology. Any deviation from perfect flatness grows exponentially over time. If the universe were slightly curved initially, it would be dramatically curved by now closed into a sphere that collapsed billions of years ago, or open into a hyperbola expanding so fast that structure couldn't form. The observed near flatness requires initial density fine-tuned to critical density within 1 part in 10 to the 60th at the Planck time, 10 to the minus 43rd seconds after the Big Bang. This fine-tuning seems implausible without explanation. Inflation solves flatness by stretching space smooth. Imagine a balloon's surface initially wrinkled and curved. Inflate the balloon to enormous size, and local regions appear flat. Curvature becomes negligible compared to the inflated radius. Similarly, inflation expanded the universe so much that any initial curvature was diluted away. The observable universe today represents a tiny patch of a vastly larger inflated region, so small that curvature is undetectable. The universe appears flat because we see only an infinitesimal fraction of its total extent, like a person on Earth's surface perceiving the ground as flat despite Earth's spherical geometry. The horizon problem concerns the CMB's uniformity. The CMB has temperature 2.7255 Kelvin everywhere, with fluctuations only 100 microkelvins, variation of only 0.004%. Yet, opposite sides of the sky regions, separated by 180 degrees, were never in causal contact according to standard Big Bang cosmology. Light from one side hasn't had time to reach the other side. The particle horizon at recombination, the farthest distance light could have travelled in 380,000 years, subtends only about 2 degrees on the sky. Regions more than 2 degrees apart should be independent, yet they have identical temperatures. How did they reach equilibrium? Inflation solves the horizon problem by positing that the observable universe was once much smaller than its causal horizon. Before inflation, all regions now visible were in thermal contact, reaching uniform temperature. Inflation then stretched this small, causally connected region to size far exceeding the particle horizon, separating previously connected regions beyond each other's horizons. The regions remained at similar temperatures because they were thermalized before inflation separated them. What appears as miraculous coordination, distant regions with identical temperatures despite no causal connection, is actually explained by prior contact before inflation. The monopole problem involves topological defects predicted by grand unified theories. These theories, attempting to unify electromagnetic weak and strong forces, predict that phase transitions in the early universe should create magnetic monopoles particles with only north or south magnetic charge, not both. The predicted monopole density is enormous, roughly 1 monopole per horizon volume at the Guts scale, 10 to the minus 35th seconds. This would produce monopole density far exceeding observed matter density. The universe would be dominated by monopoles, dramatically affecting expansion and structure formation. Yet no magnetic monopoles have ever been observed. Inflation solves monopoles by dilution. If monopoles formed before inflation, inflation diluted their density exponentially. An expansion factor of e to the 60th means monopole density decreased by factor e to the 180th, 1 part in 10 to the 78th. The observable universe might contain 0 or 1 monopole on average, explaining non-detection. Monopoles still exist somewhere in the vastly larger inflated universe, but are spread so thinly that finding one is nearly impossible. Inflation doesn't prevent monopole formation, but renders them so rare within the observable universe that absence is expected. Guth's original inflation model, old inflation, suffered from a fatal flaw, the graceful exit problem. Inflation, driven by a scalar field trapped in a false vacuum, a high-energy state that decays to true vacuum, can begin uniformly but ends through bubble nucleation. True vacuum bubbles form randomly and expand, colliding with other bubbles. These collisions create inhomogeneities far too large compared to observed CMB fluctuations. The universe emerging from old inflation would be extremely non-uniform, contradicting observations. Guth recognized this problem but couldn't solve it within the original model. Andrei Linde at the Lebedev Physical Institute in Moscow, and independently Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania, proposed new inflation in 1982, solving the graceful exit problem. Instead of first-order phase transition through bubble nucleation, new inflation features slow roll inflation. The scalar field, called the inflaton, rolls slowly down a potential energy curve. While rolling slowly, potential energy dominates, causing exponential expansion. When the field reaches the potential's minimum, inflation ends smoothly and uniformly. The field oscillates around the minimum, transferring energy to particle creation through reheating, initiating the hot Big Bang. Chaotic inflation, proposed by Linde in 1983, generalizes new inflation. In chaotic inflation, different regions of the early universe start with different inflaton field values due to quantum fluctuations. Regions where the inflaton starts high on the potential undergo inflation. The inflaton rolls down slowly, expanding that region enormously. Other regions where the inflaton starts low don't inflate. Our observable universe emerged from one region that inflated. The model is called chaotic because initial conditions are random, not fine-tuned. As long as some region somewhere starts in conditions favorable for inflation, that region inflates into a huge universe. The amount of inflation is quantified by the number of e-folds, n. Each e-fold multiplies the scale factor by e, approximately 2.718. After n e-folds, the scale factor grows by e to the n. Solving the flatness and horizon problems requires at least 60 e-folds expansion by factor e to the 60th, approximately 10 to the 26th. More e-folds are possible. Models with 100 e-folds expand by factor 10 to the 43rd. There's no upper limit. Inflation continues until the inflaton reaches the potential minimum. Eternal inflation suggests that in some regions, inflation never ends, continuing forever while spawning pocket universes where inflation terminates locally. Quantum fluctuations in the inflaton field during inflation create density perturbations, the seeds of structure formation. The inflaton, being a quantum field, exhibits vacuum fluctuations, temporary energy variations on small scales. During inflation, expansion stretches these fluctuations from quantum to cosmic scales. Fluctuations initially smaller than the Planck length, 10 to the minus 35th meters, expand to sizes larger than the observable universe. When inflation ends, these stretched fluctuations become classical density variations, regions with slightly more or less matter. Gravitational collapse amplifies these variations, forming galaxies and structure. The CMB fluctuations directly reflect inflaton quantum fluctuations. Inflation predicts a specific spectrum of density perturbations, scale invariant or nearly so, meaning fluctuations have similar amplitude at all scales. The spectral index n sub s parameterizes deviation from exact scale invariance. Perfect scale invariance gives n sub s equals 1. Inflation predicts n sub s slightly less than 1, about 0.96 to 0.97, depending on the inflaton potential's shape. Planck measurements give n sub s equals 0.9649 plus or minus 0.0042, impressively consistent with inflation's predictions and inconsistent with alternative models predicting different spectral indices. Inflation remains the leading theory for the universe's initial conditions, but it's not without challenges. The theory requires a scalar field, the inflaton with specific potential energy curve. But the inflaton hasn't been observed directly, and its identity remains unknown. Various candidates exist. A new fundamental field, the Higgs field, or fields from string theory. Additionally, inflation seems to require fine-tuning of the potential's shape to produce slow roll dynamics. Some physicists argue this replaces one fine-tuning problem, initial conditions, with another potential shape. Others counter that inflation is generic. Many different potentials produce inflation, making it less fine-tuned than alternatives. The Hubble constant measuring how fast space expands. The Hubble constant, denoted h0, measures the current expansion rate of the universe. It quantifies the relationship between distance and recession. Velocity equals h0 times distance. The constant's units are typically kilometers per second per megaparsec. 1 megaparsec equals 3.26 million light years. So h0 equals 70 kilometers per second per megaparsec means that for every 26 million light years of distance, recession velocity increases by 70 kilometers per second. Galaxies at 10 megaparsecs, 32.6 million light years, recede at 700 kilometers per second. Galaxies at 100 megaparsecs recede at 7,000 kilometers per second. Edwin Hubble discovered the expansion relationship in 1929 using observations from the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble measured distances to galaxies using Cepheid variable stars, whose period luminosity relationship, discovered by Henrietta Leavitt in 1912, provides a distance indicator. He measured velocities using redshifts of spectral lines. Light from receding galaxies shifts toward longer red wavelengths. Hubble found that more distant galaxies receded faster, with velocity proportional to distance. His initial value for the proportionality constant was about 500 kilometers per second per megaparsec, roughly 7 times larger than modern measurements due to errors in distance estimates. Hubble's original constant had large uncertainty because distance measurements were inaccurate. The Cepheid period luminosity relation used by Hubble suffered from confusion between classical Cepheids and type II Cepheids, which have different luminosities. Walter Baade resolved this in the 1950 seconds, finding that galaxies were about twice as distant as Hubble thought, reducing the constant to roughly 250 kilometers per second per megaparsec. Subsequent improvements in distance measurements continued refining the value downward. By the 1990 seconds, estimates ranged from 50 to 90 kilometers per second per megaparsec, with the HST Key project targeting reduction of uncertainties. The Hubble Space Telescope Key project on the extragalactic distance scale, led by Wendy Friedman and colleagues from 1990 to 2001, aimed to determine 0 to 10% accuracy. The project used HST to observe Cepheid variables in galaxies out to 25 megaparsecs, calibrating secondary distance indicators like type Ia supernovae and the Tully-Fisher relation for spiral galaxies. The final result, published in 2001, gave h0 equals 72 plus or minus 8 kilometers per second per megaparsec. This represented a major achievement, narrowing the decades-long controversy about the constant's value to within 10%. The Planck satellite measured h0 indirectly by analyzing the cosmic microwave background. The CMB fluctuation pattern depends on cosmological parameters, including zero, through its effect on the universe's expansion history. By fitting the observed CMB power spectrum to theoretical predictions, Planck inferred h0 equals 67.4 plus or minus 0.5 kilometers per second per megaparsec in its 2018 data release. This measurement assumes the lambda CDM model is correct. The small uncertainty, less than 1%, reflects Planck's precision, but the method depends on the model rather than directly measuring distances and velocities like Hubble did. Local measurements using the cosmic distance ladder give different values. Adam Rees at Johns Hopkins University leads the SH0ES program Supernova 0 for the equation of state using Hubble Space Telescope observations of Cepheids and type Ia supernovae. The 2022 SH0ES result gives H0 equals 73.04 plus or minus 1.04 kilometers per second per megaparsec. This value disagrees with Planck at the 5 sigma level, extremely significant statistically. 5 sigma corresponds to about 1 chance in 3.5 million of occurring randomly if the measurements truly agree. The discrepancy, called the Hubble tension, is one of cosmology's most pressing problems. Several explanations for the Hubble tension have been proposed. Systematic errors in either measurement could account for the difference. The Planck team has extensively checked for foreground contamination, instrumental issues, and analysis assumptions, finding none that explain the discrepancy. The SH0ES team has similarly checked for Cepheid calibration errors, supernova systematics, and bias from local structures like the local void. No errors large enough to resolve the tension have been found. If measurements are correct, the tension implies new physics beyond the standard lambda CDM model. Early dark energy is one proposed resolution. This hypothetical component would dominate briefly at redshifts around 1,000 to 10,000, boosting expansion during that epoch. The extra expansion would make the sound horizon at recombination smaller than lambda CDM predicts. For the observed CMB angular scale to match the smaller sound horizon requires adjusting H0 upward, potentially reconciling Planck with local measurements. Early dark energy models predict specific signatures in the CMB that Planck data constrain but don't definitively rule out. Future CMB experiments with better precision might confirm or exclude this scenario. Interacting dark energy and dark matter provide another possible explanation. If dark energy and dark matter interact exchanging energy, the interaction could alter expansion history in ways that affect H0 inferred from the CMB while leaving local distance ladder measurements unchanged. Various interaction models have been explored, some succeeding in reducing the tension but often requiring fine-tuned couplings. The physics of such interactions remains speculative, with no fundamental theory predicting them, making these models phenomenological rather than theoretically motivated. Modified gravity theories offer radical alternatives. Perhaps general relativity fails at cosmological scales, and the true gravitational theory predicts different expansion history than lambda CDM. Modifications could alter how the CMB pattern encodes H0 without affecting local measurements. But modified gravity faces severe constraints from other observations: gravitational wave, propagation speed, lensing, and structure formation all constrain deviations from general relativity to percent levels or better. Any modification must explain the Hubble tension while respecting these constraints, a difficult challenge. The Hubble time 1/H0 provides a characteristic timescale for the universe. With H0 equals 70 km per second per megaparsec, converting units gives H0 approximately 2.3 times 10 to the minus 18th per second. The Hubble time equals 1 divided by H0, approximately 4.3 times 10 to the 17th seconds, or 13.7 billion years. This is close to, but not identical to the universe's age, because expansion hasn't been constant. It decelerated during matter domination and accelerated during dark energy domination. The age is less than Hubble time in decelerating universes and more in accelerating universes. For lambda CDM, age is about 95% of Hubble time. The Hubble parameter, HT, dropping subscript 0, varies with time. Early in cosmic history, When matter and radiation densities were higher, the Hubble parameter was larger, expansion was faster. As the universe expanded and densities decreased. Recently, dark energy domination has caused to approach a constant asymptoting to the cosmological constant's value. In the far future, HT will equal roughly 56 kilometers per second per megaparsec, the expansion rate driven purely by dark energy, with matter density negligible. This asymptotic constant determines the universe's ultimate fate, eternal, exponential expansion. Future missions aim to resolve the Hubble tension. The James Webb Space Telescope, launched December 2021, observes Cepheids in galaxies beyond HST's range, extending and refining the distance ladder. The European Space Agency's Euclid mission, launched July 2023, maps galaxy distributions and weak lensing to constrain cosmological parameters, including zero, through complementary methods. NASA's Nancy Grace Roman Space Telescope, planned for 2027 launch, will observe thousands of supernovae and map cosmic structures with unprecedented precision. These missions might confirm the tension, requiring new physics, or resolve it by revealing systematic errors. The scale factor that grew 1,100 times since CMB. The scale factor, universally denoted ET, measures the universe's size as a function of time. Cosmologists normalize the scale factor to equal 1 at the present time, 8 sub 0 equals 1, so that A equals 2 means the universe is twice as large as today, and A equals 0.5 means it was half its current size. The scale factor isn't a physical size in kilometers, but rather a dimensionless quantity representing relative size. Distances between galaxies, comoving distances that factor out expansion scale proportionally with a put. If two galaxies were 100 megaparsecs apart when A equals 0.5, they're 200 megaparsecs apart now at A equals 1. At recombination, when the cosmic microwave background formed, the scale factor was approximately 0.00092. This value comes from the CMB redshift of 1090. The relationship between redshift Z and scale factor is 1 plus Z equals 1 divided by A. For Z equals 1090, we get 1091 equals 1 divided by A, giving A equals 1 divided by 1091, approximately 0.00092. The universe has expanded by a factor of 1091 since recombination distances have increased 1091-fold, and wavelengths have stretched 1091 times. The 3000 Kelvin temperature at recombination redshifted to 2.7 Kelvin today. The scale factor's time evolution determines the universe's expansion history. The Friedmann equations from general relativity govern how ET changes. The first Friedmann equation states that the quantity A dot divided by A squared equals 8 pi times Newton's gravitational constant divided by 3 times the total energy density minus k times c squared divided by A squared, where A dot is the time derivative of A and k describes curvature. For flat geometry, k equals 0, simplifying the equation. The total energy density includes contributions from matter, radiation, dark energy, and curvature. In the radiation-dominated era, roughly the first 50,000 years, energy density was dominated by photons and relativistic particles. Radiation energy density scales as 1 divided by A to the 4th power because, as space expands, both photon number density decreases going as 1 over a cubed, and each photon's energy decreases due to redshift going as 1 over A. Combined radiation energy density goes as 1 over a to the fourth. The Friedmann equation with this density gives a proportional to the square root of time. The universe doubled in size in constant time intervals. During the matter-dominated era, from 50,000 years after the Big Bang to about 9 billion years, matter density dominated. Matter energy density, mass density, times c² scales as 1 divided by a cubed. As space expands, matter dilutes the number of atoms per volume, decreases as volume increases. In the matter-dominated regime, the Friedmann equation gives a proportional to T to the 2/3 power. Expansion slowed compared to radiation domination because matter has non-relativistic velocities, contributing pressure to energy density and gravitationally decelerating expansion more than radiation does. Since about 9 billion years ago, redshift Z, approximately 0.5 dark energy, has dominated. Dark energy, represented by the cosmological constant lambda, has constant energy density that doesn't dilute with expansion. As space expands, new space carries the same dark energy density, making total dark energy increase proportionally to volume. When dark energy dominates, the Friedmann equation gives exponential expansion a proportional to e to the Haas-Rho times t. The scale factor grows exponentially, accelerating expansion. This acceleration will continue forever, assuming dark energy remains constant. The transition from deceleration to acceleration occurred at redshift Z, approximately 0.67, about 6 billion years ago. At this redshift, matter density and dark energy density were equal. For Z greater than 0.67, matter dominated and expansion decelerated due to gravitational attraction. For Z less than 0.67, dark energy dominated and expansion accelerated. The equality point shifted over time as matter diluted while dark energy remained constant. By redshift 0.67, matter had diluted enough that dark energy's repulsive effect overcame matter's attractive gravity. The scale factor's growth rate determines the Hubble parameter, h equals a dot divided by a. This is the fractional rate of change of the scale factor, how fast a increases per unit a. In the present epoch, with Hsero approximately 70 km per second per megaparsec, the universe's size increases by 0.007% per million years. This slow growth rate reflects dark energy domination. Expansion is accelerating, but currently gradual. In the far future, as matter density becomes negligible, h will approach the cosmological constant's contribution, roughly 56 km per second per megaparsec, and remain constant, pure exponential expansion. Look-back time, how long ago light was emitted from an observed object, depends on redshift through the scale factor's history. For redshift Z equals 1, the scale factor was 0.5, and look-back time is about 7.7 billion years. Light left that galaxy 7.7 billion years ago when the universe was 6 billion years old. For Z equals 2, A equals 0.33, and look-back time is 10.2 billion years. For Z equals 10, A equals 0.091, and look-back time is 13.2 billion years. The relationship is non-linear because expansion rate changed early. Expansion was faster due to higher matter density. The comoving distance in coordinates that expand with the universe, relates to scale factor through integration. The comoving distance d sub c to redshift z equals the integral from scale factor a equals 1 over 1 plus z to a equals 1 of c divided by a squared times ha, integrated over a. This integral accounts for how light traversed a universe expanding at rate HA at each scale factor. For the CMB at z equals 1090, this integral gives comoving distance 46.5 billion light-years. The physical distance when light was emitted was this comoving distance times the scale factor, then about 42 million light-years. The scale factor provides a natural time coordinate in cosmology. Instead of measuring time t since the Big Bang, cosmologists often use the scale factor a or redshift z as time variables. Physical processes depending on density or temperature automatically follow when expressed in terms of a, because densities scale as powers of a. Recombination occurred at a equals 0.00092. Big Bang nucleosynthesis, creating light elements, occurred at approximately 10 to the minus 10th. Inflation ended at a perhaps 10 to the minus 30th. Using a as time coordinate makes the physics clearer than using absolute time. Future scale factor evolution is predictable given dark energy properties. If dark energy is a cosmological constant, the scale factor will grow exponentially forever. At scale factor a equals 2, when the universe is twice its current size expected in about 10 billion years, the Hubble parameter will be roughly 60 kilometers per second per megaparsec. At a equals 10 inches 26 billion years, h will approach 56 kilometers per second per megaparsec asymptotically. Galaxies beyond the cosmic horizon will recede so fast that we'll lose causal contact, fading from view as their light gets redshifted beyond detection. If dark energy isn't constant, but varies parametrized by equation of state, W equals pressure divided by energy density, the future differs. The cosmological constant has W equals -1. Phantom dark energy with W less than -1 causes super exponential expansion. The scale factor diverges to infinity in finite time in a big rip scenario. Quintessence with -1 less than W less than -1/3 causes slower acceleration than cosmological constant. Current observations constrain W to be very close to -1 within a few percent, but leave room for slow variation. Future observations will tighten these constraints, revealing whether dark energy is truly constant. The flatness measurements showing zero curvature. The universe's spatial geometry, its curvature, is one of cosmology's fundamental properties. General relativity allows three possibilities: positive curvature, creating a closed spherical geometry; negative curvature, creating an open hyperbolic geometry; or zero curvature, creating flat Euclidean geometry. The geometry determines whether parallel lines eventually converge, diverge, or remain parallel, and whether the universe is finite or infinite in extent. Measurements from the Planck satellite published in 2018 show the universe is flat to within 0.2%. The total density parameter, omega, equals 1 ± 0.002. The density parameter omega equals the actual density divided by the critical density. The critical density is the density required for flat geometry, about 9.47 times 10 to the minus 27th kilograms per cubic meter, equivalent to about 5.7 protons per cubic meter. If omega greater than 1, the universe has positive curvature, closed spherical geometry like the three-dimensional surface of a four-dimensional sphere. If omega less than 1, negative curvature, open hyperbolic geometry like a saddle shape extending infinitely. If omega equals 1 exactly, flat geometry, ordinary Euclidean space extending infinitely. The CMB power spectrum directly measures curvature through the angular positions of acoustic peaks. Sound waves in the pre-recombination plasma created preferred scales, The sound horizon at recombination was about 490,000 light-years. This distance appears as an angle on the sky depending on the universe's geometry. In flat geometry with no curvature, light travels in straight lines, and the sound horizon subtends about 1 degree. Positive curvature acts like a converging lens, making the sound horizon appear larger peaks shift to larger angular scales. Negative curvature acts like a diverging lens, making it appear smaller. The first acoustic peak in the CMB power spectrum occurs at multipole moment approximately 220, corresponding to angular scale about 0, 8 degrees. The precise location depends on the universe's composition and geometry. For flat geometry with lambda CDM composition, theory predicts peaks at specific values. Observations match these predictions, confirming flatness. If geometry were significantly curved, the predicted peak locations wouldn't match observations regardless of composition adjustments. The peak position's sensitivity to curvature makes the CMB an excellent geometry probe. Omega total equals 1.0001 plus or minus 0.0018 according to Planck 2018 data. The uncertainty 0.0018 means curvature is constrained to less than 0.2%. This doesn't prove the universe is exactly flat. Measurements have finite precision, but any curvature is small. The curvature radius, analogous to a sphere's radius for positive curvature, must be at least 250 times the observable universe's radius, about 11,600 billion light-years. If the universe is a three-dimensional sphere, its circumference exceeds 73,000 billion light-years. The observable universe at 93 billion light-years diameter is a tiny patch of this hypersphere. Why is the universe so flat? In standard Big Bang cosmology, without inflation, flatness is unstable. Any deviation from omega equals 1 grows exponentially. If omega differed from 1 by 1 part in 10 to the 60th at the Planck time 10 to the minus 43rd seconds, it would differ by order unity by now, making the universe dramatically curved. The observed flatness requires initial omega, fine-tuned to 1 to extraordinary precision, the flatness problem. This fine-tuning seems implausible without explanation. Inflation solves the flatness problem by exponentially diluting curvature. During inflation, the scale factor increased by e to the 60th or more. Curvature contributes to the Friedmann equation through a term proportional to 1 over a squared. Inflation increases a by 10 to the 26th, so curvature term decreases by 10 to the 52nd, becoming utterly negligible. After inflation, the universe is flat to within 1 part in 10 to the 52nd, regardless of initial curvature. The observable universe represents a tiny inflated patch, so small compared to curvature radius that it appears flat, like Earth's surface appears flat locally. The flatness measurement constrains curvature, but doesn't determine its sign whether positive or negative if magnitude is small. Both small positive and small negative curvature are compatible with observations. The CMB analysis assumes lambda CDM model and fits for curvature parameter within this model. If the model is wrong, if dark energy isn't a cosmological constant, or dark matter behaves differently than assumed, the inferred curvature might change. But lambda CDM fits data extraordinarily well, making large model errors unlikely. The flatness conclusion is robust against reasonable model variations. Baryon acoustic oscillations provide an independent curvature probe. These are imprints of sound waves from the early universe frozen into the galaxy distribution. The sound horizon, at recombination 490,000 light-years, creates a preferred galaxy separation scale. This scale serves as a standard ruler. Knowing its physical size and measuring its angular size determines distance and geometry. BAO measurements from galaxy surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument agree with CMB flatness measurements, confirming the universe is flat through independent methods. The critical density can be calculated from the Hubble constant using the formula critical density equals 3 times h0 squared divided by 8 pi times Newton's gravitational constant. With h0 equals 70 km per second per megaparsec, converting units gives critical density 9.2 times 10 to the minus 27th kilograms per cubic meter. This is about 5.5 hydrogen atoms per cubic meter on average. The universe's actual density equals critical density within 0.2%, meaning space contains about 5.5 particles per cubic meter, counting all matter and dark matter, plus dark energy, equivalent to about 10 particles per cubic meter if converted to mass via E equals mc squared. Flatness implies the universe's total extent far exceeds the observable universe. In flat geometry, space extends infinitely, there's no edge or boundary. The observable universe, at 46.5 billion light-years radius, is a finite sphere within infinite flat space. Beyond the observable universe lies more space, more galaxies, more matter extending forever. We'll never observe these distant regions because light from them hasn't reached us yet and may never reach us due to accelerating expansion. The observable universe is an island of causally connected space, surrounded by unreachable expanses. If the universe has slight positive curvature, omega slightly above 1, it's a three-dimensional hypersphere, finite but unbounded. Traveling far enough in a straight line returns you to your starting point after circumnavigating the hypersphere. The minimum circumference, given omega less than 1.002, exceeds 73,000 billion light-years, 800 times the observable diameter. Even if the universe is closed, it's so large that curvature is undetectable and the finite volume vastly exceeds what we observe. Whether infinite, flat, or finite spherical, the universe extends far beyond observable limits. Future CMB experiments might tighten curvature constraints further. CMB S4, a proposed ground-based experiment, aims to measure polarization with precision, exceeding Planck by factor of 10. This would constrain omega to 0.1% if systematics can be controlled. The proposed LIGHT-BID satellite, planned by Japan Aerospace Exploration Agency for 2032 launch, would measure CMB polarization from space, with sensitivity targeting primordial gravitational waves, but also improving curvature measurements. These experiments might definitively confirm flatness to 0.01%, or potentially detect tiny curvature signaling a finite universe. The density parameters that add to exactly 1. The universe's total density divides into several components, each contributing a fraction parameterized by omega. The sum of all omega values equals the total density parameter, which measurements show equals 1 within 0.2%, confirming flat geometry. The largest component is dark energy, at omega lambda equals 0.684, comprising 68.4% of the total energy density. Dark matter contributes omega dark matter equals 0.265 or 26.5%. Ordinary baryonic matter, protons, neutrons, electrons, contributes omega baryon equals 0.049, just 4.9%. Radiation, including photons and neutrinos, contributes roughly 0.01%, negligible at present, though dominant in the early universe. These values come from Planck satellite measurements, published in 2018, representing the most precise determination of cosmic composition. The measurements combine CMB temperature and polarization data with constraints from baryon acoustic oscillations and other cosmological probes. The uncertainties are remarkably small. Dark energy density is known to 1%, dark matter to 1.5%, and baryonic matter to 2%. This precision represents decades of observational and theoretical work, transforming cosmology from a qualitative science to a precision science, with parameters measured to percent-level accuracy. Dark energy density remains constant as the universe expands. Its equation of state parameter W approximately equals -1, characteristic of a cosmological constant. As space expands, dark energy density stays fixed at about 6 × 10⁻⁻10th joules per cubic meter. The total dark energy increases proportionally to volume because new space carries the same energy density. This constant density drives accelerated expansion. While matter dilutes as the universe expands, dark energy doesn't. So its relative importance grows until it dominates, which happened about 5 billion years ago at redshift Z, approximately 0.5. Dark matter density scales as 1 divided by a cubed, where A is the scale factor. As space expands, dark matter particle number remains constant, but volume increases, so density decreases. At redshift Z equals 1, when the scale factor was 0.5, dark matter density was 8 times higher than today, scaling as 1 over 0.5 cubed equals 8. At recombination, when A equals 0. 0.00092, dark matter density was 1.3 million times today's value. Despite this dilution, dark matter dominated the universe's energy density from about 50,000 years after the Big Bang until 9 billion years ago, driving structure formation during this crucial epoch. Baryonic matter, ordinary atoms and ions, also scales as 1 over a cubed, diluting identically to dark matter. The baryon to dark matter ratio, omega baryon divided by omega dark matter, equals about 0.185 and remains constant throughout cosmic history. For every 5.4 dark matter particles, there's 1 baryon. This ratio is fundamental, set during Big Bang nucleosynthesis when protons and neutrons formed from the quark-gluon plasma. The ratio depends on the universe's baryon to photon ratio, about 6 × 10⁻⁻10th, which determines how many baryons survived annihilation with antibaryons in the first seconds. The critical density, 9.47 × 10⁻27th kilograms per cubic meter, serves as the reference for all omega values. Dark energy contributes 6.48 × 10⁻27th kilograms per cubic meter in equivalent mass through E equals mc². Dark matter contributes 2.51 × 10⁻27th kilograms per cubic meter. Baryonic matter contributes 4.6 × 10⁻28th kilograms per cubic meter, about 0.28 hydrogen atoms per cubic meter on average throughout space. These densities are extraordinarily low by terrestrial standards. Interstellar space contains about 1 atom per cubic centimeter, roughly 10 to the 6th times denser than the cosmic average. Radiation energy density photons and relativistic particles contributes omega radiation approximately 5 × 10⁻⁵ at present, utterly negligible. But radiation scales as 1 over A to the 4th power because both number density and individual photon energy decrease with expansion. At early times, when A was small, radiation dominated. At redshift, Z equals 3200, corresponding to scale factor A equals 0.0003. Radiation density equaled matter density. Before this equality, radiation dominated, and the universe expanded according to radiation-dominated dynamics, with scale factor proportional to square root of time. The cosmic microwave background photons, the most numerous radiation component, have number density about 410 photons per cubic centimeter. Each photon has average energy about 2.4 times 10 to the minus 4th electron volts, corresponding to 2.7 Kelvin temperature. The total energy density is number density times average energy, giving about 4 times 10 to the minus 14th joules per cubic meter. Converting to equivalent mass via E equals mc squared gives 4.5 times 10 to the minus 31st kilograms per cubic meter, about 100,000 times less than baryonic matter. Photons filled the early universe, but now are energetically irrelevant. Neutrinos contribute omega neutrino approximately 0.001 to 0.002, depending on neutrino masses, which remain uncertain. Neutrinos are the second most abundant particles after photons, with number density about 340 neutrinos per cubic centimeter, slightly less than photons because neutrinos decoupled earlier when the universe was hotter, and subsequent electron-positron annihilation reheated photons but not neutrinos. Neutrino masses are small total mass of all three flavors is less than 0.12 electron volts based on cosmological constraints, but non-zero, making neutrinos contribute to matter density slightly. The sum omega lambda plus omega dark matter plus omega baryon plus omega radiation plus omega neutrino equals 1 within observational uncertainties, confirming flat geometry. This equality isn't coincidental, it reflects the universe's geometry. In flat universe, total density must equal critical density by definition. The fact that measurements of independent components sum to the critical density validates both the measurements and the geometric interpretation. If components didn't sum to 1, either measurements would be wrong or geometry would be curved contrary to CMB peak positions. The composition's evolution determines cosmic history. In the first 50,000 years, radiation dominated with omega radiation, approximately 1 and others negligible. From 50,000 years to 9 billion years, the matter-dominated era omega matter approximately equaled 1, with dark matter dominating over baryons. During this era, structures formed as dark matter gravitationally collapsed, pulling baryons into growing concentrations that became galaxies. Since 9 billion years ago, dark energy has dominated, with omega lambda rising above 0.5 and now at 0.68. Future evolution will see matter density continuing to decrease, while dark energy remains constant, asymptotically approaching omega lambda equals 1. Measuring these densities requires multiple probes. The CMB constrains the matter-radiation ratio at recombination through damping tail, small-scale fluctuations erased by photon diffusion. Big Bang nucleosynthesis constrains baryon density through light element abundances. More baryons produce more helium-4 and less deuterium. Galaxy surveys constrain matter density through clustering. Amplitude, more matter creates stronger clustering. Supernovae constrain dark energy through luminosity distances. Combining probes breaks degeneracies, allowing independent determination of each component's density. The concordance of different measurement methods is striking. CMB-derived baryon density agrees with Big Bang nucleosynthesis at 2% level, remarkable given completely different physics. CMB-derived matter density agrees with galaxy clustering and weak gravitational lensing at 5% level. Dark energy density inferred from CMB agrees with supernova measurements at 3% level. This concordance wasn't guaranteed. Independent methods could have disagreed, requiring model revisions. The agreement validates lambda CDM as the correct description of cosmic composition. Dark matter remains mysterious despite comprising 26.5% of the universe. Its identity is unknown. Candidates include weakly interacting massive particles, or WIMPs, axions, sterile neutrinos, or primordial black holes. Dark matter interacts gravitationally, but not electromagnetically, making it invisible except through gravitational effects on galaxies, galaxy clusters, and the CMB. Multiple lines of evidence confirm its existence. Galaxy rotation curves, cluster mass profiles, gravitational lensing, and CMB acoustic peaks all require dark matter. Yet decades of direct detection experiments have failed to identify the particles, making dark matter cosmology's greatest mystery. The curvature radius of at least 250 times observable universe. The universe's curvature radius, if space is curved rather than perfectly flat, must exceed 250 times the observable universe's radius based on Planck satellite measurements. The observable universe has radius 46.5 billion light-years, so the minimum curvature radius is 11,600 billion light-years, or 11.6 trillion light-years. If the universe is a three-dimensional hypersphere, the curved space analogue of a sphere's two-dimensional surface, its total circumference exceeds 73 trillion light-years. This minimum size applies if the universe has positive curvature. For negative curvature, forming hyperbolic space, the universe extends infinitely, but with curvature scale exceeding 250 observable radii. The curvature radius relates to the density parameter through omega k equals negative k times c squared divided by a squared times h0 squared, where k is the curvature parameter from general relativity. For flat space, k equals 0 and omega k equals 0. Positive curvature has k equals positive 1 and omega k less than 0. Negative curvature has k equals negative 1 and omega k greater than 0. Planck measurements give omega k equals 0.001 plus or minus 0.002, constraining curvature to within 0.2% of flat. This constraint translates to curvature radius exceeding about 250 times the Hubble radius c divided by H0. Why 250 specifically? The Hubble radius equals c divided by H0, approximately 14 billion light-years, slightly less than the particle horizon at 46.5 billion light-years. The curvature constraint from CMB measurements gives absolute value of omega k less than 0.002. The curvature radius, in units of Hubble radius, equals 1 divided by the square root of the absolute value of omega k. For omega k equals 0.002, this gives 1 divided by the square root of 0.002, approximately 22. But this is in Hubble radii. Converting to observable universe radii, which are 3.3 times larger than Hubble radii, gives a factor around 250. Different analyses give somewhat different factors, but all agree the minimum radius greatly exceeds the observable universe. If the universe is a hypersphere with curvature radius 250 times the observable radius, travelling in a straight line would eventually return you to your starting point after covering a distance equal to the circumference 2 pi times the curvature radius. For curvature radius 11,600 billion light-years, the circumference is 73,000 billion light-years. At light speed, circumnavigating the universe would take 73 trillion years, 5,000 times longer than the universe's current age. Even at light speed, travelling around the universe is utterly impractical. Moreover, accelerating expansion driven by dark energy will make circumnavigation impossible. The expansion rate would carry you away from your starting point faster than you approach it. The minimum size constraint applies regardless of curvature sign. For negative curvature hyperbolic space, the universe is infinite, but the curvature scale, analogous to radius for positive curvature, must exceed 250 observable radii. Hyperbolic space curves away from itself rather than curving back like a sphere, creating infinite extent. The curvature scale determines how rapidly space curves. Large curvature scale means gentle curvature, locally appearing very flat. The constraint that curvature scale exceeds 250 observable radii means curvature is so gentle that the observable universe appears flat to high precision. The true size could vastly exceed the minimum. The constraint gives a lower bound curvature radius is at least 250 times observable radius. But it could be 1,000 times larger, or 1,000,000 times, or infinite. Measurements can't distinguish between very large, finite universe and infinite universe. Both appear flat to current precision. If curvature radius is 10,000 times observable radius, the universe contains volume 10,000 cubed, 1 trillion times the observable volume. If radius is 1,000,000 times larger, volume exceeds observable volume by factor 10 to the 18th a billion billion. Each doubling of curvature radius multiplies total volume by 8. Inflation theory predicts much larger minimum sizes. Inflation expanded the early universe by at least e to the 60th factor, 10 to the 26th. Regions initially within causal contact small enough to thermalize and reach uniform temperature were stretched to size far exceeding today's observable universe. The total inflated volume exceeds the observable volume by at least 10 to the 78th, the cube of 10 to the 26th. This implies the universe contains at least 10 to the 78th observable universe-sized regions beyond what we see. More inflation, say 70 or 100 e-folds, produces proportionally larger volumes with correspondingly more unobservable regions. The curvature constraint tightens with better measurements, but will never prove exact flatness. Future experiments might measure omega k to 0.0001, pushing the minimum curvature radius to 500 or 1,000 observable radii. But proving omega k equals exactly 0 requires infinite precision unattainable with any finite measurement. The universe could have tiny curvature radius 1 trillion times observable radius that would never be detected. Whether the universe is exactly flat or merely appears flat due to enormous size remains philosophically interesting but observationally indistinguishable. Topological possibilities complicate size estimates. Even in flat geometry, the universe might have non-trivial topology identify opposite edges, like a video game, where exiting the right side returns you to the left. A flat torus topology would make the universe finite despite flat geometry. The smallest such universe, where light circumnavigates and returns, would show repeated images of galaxies as we see the same objects from different directions. Searches for these repeating patterns in galaxy distributions and CMB have found nothing, constraining the minimum size to exceed at least the observable universe. but larger topologically non-trivial spaces remain possible. Cosmic crystallography, searching for repeating patterns in galaxy positions, could detect finite topology. If the universe repeats, with period L smaller than the observable diameter, identical galaxy configurations would appear separated by distance L. Statistical analysis of galaxy surveys looking for such patterns has found no evidence setting lower limits on topological scale. The limits vary, with topology type some are constrained to exceed 25 billion light-years, others less well constrained. These limits assume specific topologies. Infinitely many topologies exist, and searching for all is impossible. The practical implication: the universe extends far beyond observation. Whether it's 250 times larger, 10 to the 26th times larger from minimal inflation, or infinite, the conclusion is the same. The observable universe represents a tiny fraction of totality. Galaxies, structures, and volumes beyond the cosmic horizon vastly outnumber what we see. These regions are real. Space exists there. Matter occupies it. Galaxies form and evolve, but they're forever beyond our observational reach. Unless faster than light, travel becomes possible. The observable universe is our cosmic island, surrounded by unobservable vastness. Some physicists argue the unobservable universe doesn't meaningfully exist. Only the observable universe matters for physics. But general relativity describes space-time everywhere, not just in the observable region. The same equations governing evolution here apply everywhere. Unless observation magically brings space into existence, a dubious philosophical position space beyond the horizon is as real as space here. We can't measure it directly, but we can infer its properties from local measurements and theory. The true size exceeds the minimum by unknown amounts, potentially infinitely. Future observations will tighten curvature bounds, but won't reveal the true size. If omega k is measured to be 0.0001 instead of 0.001, the minimum curvature radius increases from 250 to about 800 observable radii. Each order of magnitude improvement in omega k precision multiplies the minimum size by roughly 3. But reaching omega k equals 10 to the minus 6th curvature radius, exceeding 80,000 observable radii, seems beyond foreseeable experiments. Even then, the true size could be far larger. Measuring curvature provides lower bounds, but upper bounds require detecting curvature, which we can't if it's too small. The universe's true extent remains unknown and perhaps unknowable. The last scattering surface 46 billion light-years away. The cosmic microwave background originates from the surface of last, scattering a spherical shell centered on us, where photons last interacted with matter before traveling freely to us. This surface lies at comoving distance 46.5 billion light-years, essentially coincident with the particle horizon defining the observable universe's edge. The surface represents the farthest we can see using photons because before recombination at 380,000 years, the universe was opaque. Photons scattered continuously off free electrons, making the pre-recombination universe like fog. Looking into it shows only glowing fog, not individual distant objects. The last scattering surface is this fog's boundary, beyond which we cannot see with electromagnetic radiation. When photons we observe today last scattered, they were at distance only 42 million light-years from our location, vastly closer than their current 46.5 billion light-year distance. The scale factor at recombination was 0.00092, so proper distances then was 0.00092 times comoving distances. The comoving distance to the last scattering surface is 46.5 billion light-years. Multiply by 0.00092 gives 42 million light-years. These photons began their journey toward us when the universe was only 380,000 years old. They've been travelling for 13.8 billion years. The light travel time equals the universe's age, while cosmic expansion carried their origin points to 46.5 billion light-years away. The surface has finite thickness recombination, wasn't instantaneous, but occurred over several thousand years. The duration of recombination, the transition from ionized plasma to neutral atoms, was roughly 100,000 years, centered on 380,000 years after the Big Bang. During this transition, the universe gradually became transparent as free electron density decreased. The last scattering surface has thickness corresponding to this 100,000-year duration, which in comoving distance is about 400 million light-years. This thickness is much smaller than the surface's radius, so treating it as an infinitesimally thin shell is accurate for most purposes. Every observer sees their own last scattering surface centered on themselves at comoving distance 46.5 billion light-years. An observer on a galaxy currently at comoving distance 10 billion light-years from us sees a last scattering surface centered on them, overlapping but distinct from ours. The overlap includes regions visible to both observers to places on both last scattering surfaces. The non-overlapping parts include regions visible only to us or only to them. Each observer has access to different regions of the early universe through their CMB observations, though all regions have statistically similar properties due to inflation-generated uniformity. The surface's temperature when photons last scattered was approximately 3000 Kelvin, hot enough to glow orange-red like a low-temperature incandescent bulb. The entire universe at that epoch was filled with glowing gas at this temperature, appearing uniformly bright from any vantage point. An observer at recombination would see glowing fog in all directions, with temperature 3000 Kelvin. As the universe expanded and cooled, the temperature redshifted to 2.7 Kelvin, shifting the spectrum from visible light to microwaves. The glow remains uniform every direction, shows 2.7 Kelvin radiation, but wavelengths stretched 1091-fold. The surface's angular area on the sky equals 4 pi steradians, the entire sky. Every direction we look, we see photons from the last scattering surface. Nearby galaxies lie between us and the surface. We see them projected against the CMB background. Distant galaxies at redshift Z, greater than 1090, would lie beyond the surface, but such galaxies don't exist. Stars and galaxies didn't form until tens to hundreds of millions of years after recombination. The farthest observed galaxies have redshift around 13 to 14, corresponding to 300 to 400 million years after the Big Bang, long after recombination. Mapping the surface's temperature reveals fluctuations, hot and cold spots, varying by roughly 100 microkelvins around the average 2,725,000 microkelvins. These fluctuations reflect density variations in the matter distribution at recombination. Denser regions, where matter was slightly more concentrated, appear as cold spots because photons climbing out of these overdensities' gravitational potential wells lose energy through gravitational redshift. Underdense regions appear as hot spots. The fluctuation amplitude, about 1 part in 30,000, was tiny but sufficient to seed structure formation through gravitational collapse over billions of years. The fluctuation pattern across the surface is not random but structured. Acoustic oscillations in the pre-recombination plasma created preferred scales, wavelengths corresponding to peaks and troughs of sound waves that fit integer numbers of oscillations within the sound horizon. The sound horizon, how far sound waves travelled in the 380,000 years before recombination, was about 490,000 light-years. This scale and its harmonics appear as peaks in the fluctuation power spectrum at specific angular scales. The first peak at 1 degree angular scale corresponds to the sound horizon. Subsequent peaks at smaller scales correspond to harmonics. Polarization of CMB photons provides additional information about the last scattering surface. Scattering of photons off electrons at last scattering polarizes the light perpendicular to the scattering plane. The polarization pattern depends on the velocity field of matter at recombination. Moving plasma creates anisotropic radiation that polarizes scattered photons. The polarization pattern divides into E modes and B modes. E modes, detected by multiple experiments, confirm the scattering origin and provide additional constraints on cosmological parameters. B modes from primordial gravitational waves haven't been definitively detected, though searching continues. The surface is moving away from us faster than light speed due to cosmic expansion. The recession velocity equals the Hubble parameter times distance. At 46.5 billion light-years distance, with H0 approximately 70 km per second per megaparsec, the recession velocity is about 2 times light speed. This doesn't violate relativity. Space itself expands, carrying the surface away. The surface continues receding faster than light. As time passes, light from progressively later epochs reaches us, so the surface we observe gets closer in time, representing later cosmic epochs, but farther in co-moving distance, because the particle horizon grows as more time passes for light to travel. The surface temperature cools as the universe expands. Currently at 2.7255 Kelvin, the temperature decreases inversely with the scale factor. When the scale factor doubles, expected in about 10 billion years, the temperature will be 1.36 Kelvin. After another doubling in 14 billion years, it will be 0.68 Kelvin. Asymptotically, as the universe expands forever under dark energy domination, the CMB temperature approaches zero, never reaching it but becoming arbitrarily cold. In 100 billion years, the temperature will be 0.28 Kelvin. In a trillion years, 0.0027 Kelvin, 1,000th its current value. Observing the surface provides a unique cosmological probe. Unlike galaxies or quasars that are individual objects with intrinsic variability and complex evolution, the last scattering surface is a nearly uniform thermal snapshot of the universe at a single epoch. The fluctuations arise from simple physics, gravitational collapse, and acoustic oscillations, making theoretical predictions robust. Comparing predictions to observations tests cosmological models with minimal astrophysical uncertainties. This makes the CMB the gold standard cosmological probe, driving measurements of cosmic age, composition, geometry, and inflation. Future CMB observations will map the surface with increasing precision. Ground-based experiments like the Simons Observatory in Chile and the South Pole Telescope target polarization measurements, improving constraints on inflation and neutrino mass. Space missions, like the proposed CMB-HD, would measure temperature and polarization at arc-minute resolution 10 times better than Planck, revealing smaller scale structures and improving measurements of matter distribution at recombination. These observations will refine our understanding of the surface, the early universe, and the cosmological parameters that describe cosmic evolution. The acceleration discovered in 1998 supernova observations. In 1998, Two independent teams announced that the universe's expansion is accelerating rather than decelerating, a discovery that shocked the physics community and ultimately earned the 2011 Nobel Prize in Physics. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt at Australian National University and Adam Rees at Johns Hopkins University, both used Type Ia supernovae as standard candles to measure cosmic distances. They found distant supernovae appeared fainter than expected, indicating they were farther away than predicted by models. Assuming deceleration, implying expansion has been speeding up for the past several billion years. Type Ia supernovae are exploding white dwarf stars that reach nearly identical peak luminosity regardless of location, making them excellent distance indicators. The explosion occurs when a white dwarf, a stellar remnant supported by electron degeneracy pressure, accumulates matter from a companion star and exceeds the Chandrasekhar limit of 1.4 solar masses. The white dwarf collapses, igniting carbon and oxygen fusion that burns in a runaway thermonuclear explosion, completely disrupting the star. Because the explosion occurs at a well-defined mass limit, peak luminosity is standardizable, about 5 billion times the Sun's luminosity, allowing distance measurement by comparing apparent and absolute luminosity. The Supernova Cosmology Project's 1998 paper, published in the Astrophysical Journal, presented observations of 42 Type Ia supernovae at redshifts between 0.18 and 0.83. The High-Z team's 1998 paper in the Astronomical Journal presented 16 supernovae at similar redshifts. Both teams found that supernovae at redshift around 0.5, corresponding to about 5 billion years ago, were about 25% fainter than predicted by decelerating models with matter density equal to critical density. The dimming corresponded to extra distance of roughly 10 to 15% compared to deceleration predictions, requiring accelerating expansion to explain. The finding contradicted expectations. Standard Big Bang cosmology, with only matter-predicted deceleration, gravitational attraction between matter should slow expansion over time. Models with different matter densities predicted different deceleration rates, but all predicted slowing. Acceleration required something new, either a cosmological constant, Einstein's lambda, representing vacuum energy, or dynamical dark energy with negative pressure. The supernova observations, combined with CMB measurements indicating flat geometry and matter density, about 30% of critical density, implied the remaining 70% was dark energy driving acceleration. The cosmological constant provides the simplest explanation. Einstein introduced lambda into his gravitational field equations in 1917 to allow static universe solutions. The expansion of the universe hadn't been discovered yet. Lambda represented vacuum energy with constant density and negative pressure, creating gravitational repulsion that could balance matter's gravitational attraction. After Hubble discovered expansion in 1929, Einstein reportedly called lambda his greatest blunder. Expansion made static solutions unnecessary. But lambda remained a valid term in general relativity, only its value needed to be 0 or very small for consistency with observations. The supernova data required lambda approximately 0.7 times the critical density with equation of state W approximately -1, where W equals pressure divided by energy density. For W equals -1, pressure equals negative energy density, a bizarre property unique to vacuum energy or cosmological constant. This negative pressure creates repulsive gravity according to general relativity. The gravitational field depends not just on energy density, but also on pressure through the quantity energy density plus 3 times pressure. For W equals -1, this quantity is negative, producing repulsion that accelerates expansion. The High Z team's key paper, describing the discovery, published February 1998, noted that observations preferred cosmologies with positive cosmological constant over matter-only models, at confidence exceeding 99%. They wrote, "The data are consistent with a cosmological constant. The data suggest that the universe has been accelerating for approximately the past 5 billion years." Perlmutter's team published their analysis in June 1998, confirming acceleration independently. The two teams, working competitively, had checked each other's results through independent observations and analysis, strengthening confidence in the discovery. Systematic errors were thoroughly investigated. Could dust between us and distant supernovae dim them, mimicking greater distance? Dust extinction preferentially absorbs blue light, reddening the spectrum. Observations at multiple wavelengths showed distant supernovae weren't significantly redder than nearby ones, ruling out dust as explanation. Could evolutionary effects distant supernovae being intrinsically different from nearby ones because we observe them as they were billions of years ago explain the dimming? Studies of supernova properties versus redshift found no evolution sufficient to explain observations. Gravitational lensing, variable intergalactic absorption, and selection biases were all examined and excluded. Subsequent observations confirmed acceleration. The ESSENSE project from 2002 to 2008 observed 200 Type Ia supernovae at redshifts 0.2 to 0.8. The SNLS Supernova Legacy Survey observed 500 supernovae from 2003 to 2008. The Pan-STARRS survey beginning in 2010 discovered thousands of supernovae. All results confirmed the 1998 discovery expansion is accelerating, requiring dark energy comprising roughly 70% of cosmic energy density. The consistency across multiple surveys with different telescopes, analysis methods, and supernova samples left no doubt. Acceleration is real. The acceleration history reveals that expansion hasn't always accelerated. Supernovae at very high redshift above Z, approximately 1.5, corresponding to more than 9 billion years ago, are slightly brighter than pure acceleration models predict, indicating deceleration at earlier times. This matches expectations. When the universe was denser, matter dominated over dark energy, causing deceleration. Around redshift Z, approximately 0.67, about 6 billion years ago, matter density and dark energy density were equal. For higher redshifts, matter dominated and expansion decelerated. For lower redshifts, dark energy dominated and expansion accelerated. We live in the acceleration epoch, which began relatively recently in cosmic history. The 2011 Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees for the discovery. The prize citation read, "For the discovery of the accelerating expansion of the universe through observations of distant supernovae. This discovery transformed cosmology, establishing dark energy as a fundamental cosmic component. It also posed profound questions. What is dark energy? Why does it have the density it does? Why did acceleration begin only recently rather than earlier or later? These questions drive ongoing research, with dark energy remaining one of physics's greatest mysteries. Alternative explanations to dark energy have been proposed. Modified gravity theories suggests that general relativity fails at cosmological scales, and acceleration reflects not dark energy, but gravitational physics beyond Einstein's theory. But modified gravity must match general relativity's successes in solar system tests, binary pulsars, and gravitational waves, while producing acceleration. This proves difficult. Most modified gravity theories have been ruled out by observations, particularly the 2017 gravitational wave detection from neutron star merger that constrained gravitational wave speed to equal light speed to 1 part in 10 to the 15th, eliminating many modifications. Dark energy remains the simplest explanation consistent with all data. The discovery's impact extends beyond cosmology. It confirmed that cosmological constant long thought irrelevant plays a crucial role in cosmic evolution. It established that the universe contains energy of unknown nature comprising most of its energy budget. It showed that acceleration implies a far future where galaxies beyond our local group recede faster than light, disappearing beyond our cosmic horizon. The discovery opened new questions and research directions that will occupy physicists for decades, making 1998 a watershed year when cosmology took an unexpected turn. The dark energy driving expansion faster. Dark energy is the name given to whatever causes cosmic acceleration, roughly 68% of the universe's total energy density. The simplest explanation is Einstein's cosmological constant, lambda, representing vacuum energy, energy inherent to empty space itself that doesn't dilute as space expands. The energy density is approximately 6 times 10 to the minus 10th joules per cubic meter, extraordinarily small by particle physics standards, but large enough to dominate cosmic dynamics at late times. This constant energy density creates negative pressure, equaling negative energy density pressure is negative 6 times 10 to the minus 10th joules per cubic meter, causing gravitational repulsion that accelerates expansion. The cosmological constant appears in Einstein's field equations as lambda times the metric tensor on the left side, or equivalently as a stress energy tensor with constant energy density and negative pressure on the right side. The two formulations are mathematically equivalent. Lambda has units of inverse length squared. In cosmological units, lambda equals 3 times h0 squared times omega lambda, where h0 is the Hubble constant, and omega lambda equals 0.684. With h0 approximately 70 kilometers per second per megaparsec, lambda equals approximately 1.1 times 10 to the minus 52nd per meter squared, an extraordinarily small number reflecting dark energy's feeble density compared to microscopic scales. Why does vacuum have energy? Quantum field theory predicts that empty space contains zero-point energy. The lowest possible energy state still has fluctuating quantum fields. Each quantum field contributes energy density equal to 1/2 times h bar times omega summed over all field modes, where omega is the mode's frequency and h bar is Planck's reduced constant. This sum diverges infinite energy, but imposing an ultraviolet cutoff at some maximum energy scale, perhaps the Planck scale, gives finite energy density. The problem: calculating vacuum energy this way gives density about 10 to the 120th times larger than observed dark energy, the worst prediction in physics history. The cosmological constant problem asks why lambda is so small. Naively, vacuum energy should be enormous. Quantum field theory predicts energy density around 10 to the 113th joules per cubic meter if cut off at the Planck scale. The observed value is 10 to the minus 9th joules per cubic meter smaller by factor 10 to the 122nd. Some unknown mechanism must cancel vacuum energy to 122 decimal places while leaving a tiny residual equal to observed dark energy. No satisfactory explanation exists. Proposed solutions include anthropic reasoning. Only universes with small lambda allow galaxy formation, and observers or yet unknown symmetries that force lambda towards zero without reaching it. Dynamical dark energy models propose that acceleration isn't caused by a true cosmological constant, but by a scalar field called quintessence, with slowly varying energy density and pressure. The field has a potential energy curve. As the field evolves down the curve, its energy density decreases while remaining larger than matter density, driving acceleration. Different potential shapes predict different evolution histories and equation of state parameters W that might vary with time. Current observations constrain W to be very close to -1 within a few percent, but allow for slow variation. Future observations might detect time-varying W, distinguishing quintessence from cosmological constant. The equation of state parameter W determines acceleration strength. For cosmological constant, W equals exactly -1. For quintessence, W typically lies between -1 and -1/3. The value W equals -1/3 is critical. More negative values cause acceleration. Less negative values cause deceleration. Current measurements from combining supernovae, CMB, and baryon acoustic oscillations give W equals -1.03 plus or minus 0.03, consistent with cosmological constant but with room for small deviations. Phantom dark energy with W less than -1 would cause superacceleration, leading eventually to Big Rip. The universe tears itself apart in finite time. Dark energy's density has been nearly constant throughout cosmic history, despite the universe expanding by factor 1091 since recombination. Matter density decreased by factor 1.3 billion, the cube of 1091 over the same period. This means dark energy's fractional contribution changed dramatically. At recombination, dark energy comprised only 0.00000026% of total density, completely negligible. Matter dominated by 100,000 to 1 over dark energy. But matter diluted while dark energy remained constant, so dark energy's fractional share grew. Around redshift Z, approximately 0.676 billion years ago, dark energy overtook matter, beginning the dark energy-dominated epoch. Why did dark energy dominate only recently? This coincidence problem puzzles cosmologists. If dark energy is truly constant, its density was fixed throughout history, while matter density decreased. Given these different scaling laws, dark energy must dominate eventually. But why does domination occur near the present epoch rather than much earlier or later? The time when dark energy equals matter density, the transition from deceleration to acceleration, is comparable to the time when complexity arises stars, planets, life. This might be coincidence or might reflect anthropic selection. Observers can only exist in epochs allowing structure formation, which requires matter dominance early, but dark energy domination not too early. Future dark energy observations will come from multiple probes. The Dark Energy Survey used a 570 megapixel camera on the Blanco 4-meter telescope in Chile from 2013 to 2019, mapping 300 million galaxies to measure cosmic structure growth. Dark energy affects how fast structures grow. The Dark Energy Spectroscopic Instrument, or DESI, operating since 2021 on the Male 4-meter telescope in Arizona, measures redshifts for 40 million galaxies, mapping baryon acoustic oscillations to trace expansion history with unprecedented precision. ESA's Euclid mission, launched July 2023, maps galaxy clustering and weak gravitational lensing over 1/3 of the sky. NASA's Nancy Grace Roman Space Telescope, launching in 2027, will observe thousands of Type Ia supernovae to refine the expansion history and search for time variation in dark energy equation of state. Roman will also measure weak lensing, the subtle distortion of galaxy shapes, by intervening matter, mapping dark matter distribution, and testing whether dark energy affects structure formation as predicted. These missions together will determine W to 1% precision and might detect time variation, distinguishing cosmological constant from dynamical dark energy and providing clues to dark energy's nature. Modified gravity provides an alternative to dark energy. Perhaps general relativity fails at cosmological scales, and acceleration results from gravitational physics beyond Einstein, rather than from new energy component. The DGP-modelled Valley-Gabadadze-Porati, proposed in 2000, suggests gravity leaks into extra dimensions at large scales, weakening gravitational attraction and mimicking dark energy. FR gravity replaces the Einstein-Hilbert action with a function of the Ricci scalar, modifying gravitational field equations. These theories face stringent constraints from gravitational wave observations that demand gravitational wave speed equal light speed to exquisite precision, ruling out many modifications. The dark energy domination will continue forever, assuming it's a cosmological constant. As the universe expands, matter density decreases towards zero, while dark energy remains constant. Asymptotically, Omega Lambda approaches one pure dark energy universe. Expansion becomes exponential, with constant Hubble parameter h asymptoting to the square root of lambda divided by 3, approximately 56 km per second per megaparsec. Structures beyond the local group, gravitationally bound to us, will recede faster than light, crossing beyond our cosmic event horizon and disappearing from view. In hundreds of billions of years, the Milky Way, Andromeda, and local galaxies will be alone in an otherwise empty, observable universe. Dark energy represents cosmology's deepest mystery. We know it exists from observations, supernovae, CMB, structure growth, but we don't know what it is. The simplest explanation, cosmological constant, works perfectly to match data, but suffers from the cosmological constant problem, requiring extreme fine-tuning without explanation. Alternative explanations, quintessence. Modified gravity avoid some fine-tuning, but introduce complexity and remain consistent with data only because current measurements have limited precision. Resolving dark energy's nature is a primary goal of 21st century cosmology, requiring improved observations and possibly revolutionary theoretical insights. The event horizon beyond which we'll never see. The event horizon in cosmology, distinct from black hole event horizons, is the boundary beyond which light emitted today will never reach us due to accelerating expansion. The event horizon currently lies at comoving distance, approximately 16 billion light-years, much closer than the particle horizon at 46.5 billion light-years. The difference: the particle horizon includes regions whose light has reached us from the past, while the event horizon includes only regions we could theoretically reach by sending a light speed signal today. Galaxies beyond the event horizon are causally disconnected from our future. We cannot affect them, and events occurring there now will never influence us. The event horizon's location depends on dark energy properties. For a cosmological constant with equation of state W equals -1, the event horizon sits at comoving distance approximately 16 billion light-years, about 1/3 the particle horizon distance. For phantom dark energy with W less than -1, causing superacceleration, the event horizon is closer, perhaps 10 billion light-years or less, depending on W's value. For quintessence with W greater than -1, the event horizon is farther than 16 billion light-years, and might not exist at all if dark energy eventually becomes negligible, returning to deceleration. The horizon's existence and location directly reflect dark energy's influence on future expansion. Light emitted today from galaxies beyond the event horizon will never reach us no matter how long we wait. The reason? These galaxies recede so fast that even light travelling toward us at sea makes no progress against expansion. Imagine walking on a treadmill, moving faster than you can walk. You walk forward but move backward relative to the ground. Similarly, light from distant galaxies travels toward us at sea, but space expands faster, carrying the light away. The event horizon marks the distance where this balance occurs. Recession velocity exactly equals c. Beyond this distance, recession exceeds c, and light moves away from us, despite propagating toward us through space-time. The event horizon shrinks in comoving coordinates as time passes. Currently at 16 billion light-years, it will shrink to perhaps 12 billion light-years in 10 billion years, then 8 billion light-years in 20 billion years, asymptotically approaching the Hubble radius c divided by h infinity about 5.3 billion light-years in the far future. The shrinking means galaxies currently inside the event horizon will cross outside as time passes, becoming unreachable. A galaxy at comoving distance, 15 billion light-years today, is inside the horizon. Light we send now could reach it, but in 20 billion years it will be outside, beyond reach forever. The observable universe will become progressively isolated. Galaxies between the particle horizon and event horizon, distances 16 to 46.5 billion light-years, are visible now but unreachable. We receive light they emitted billions of years ago when they were closer and inside the event horizon. Their ancient light reached us, but light emitted now from their current locations will never reach us. These galaxies are visible ghosts. We see their pasts, but cannot see their presents or futures. As time passes, these galaxies fade and redshift beyond detection, disappearing from view. Their disappearance doesn't mean they cease existing, but simply that causal contact is lost. They continue evolving beyond observation. The proper distance to the event horizon, the distance measured by a chain of rulers at a single moment, is about 16 billion light-years. But recession velocity at this distance is v equals h times d equals 70 kilometers per second per megaparsec times 4,900. Megaparsecs equals 343,000 kilometers per second, about 1.14 times light. Speed. This exceeds c because space expansion isn't constrained by relativity's speed limit. Objects can't move through space faster than light, but space itself can expand at any rate. At the event horizon, expansion exactly equals light speed balanced, such that light emitted toward us remains at constant proper distance despite travelling at sea. The cosmological event horizon differs fundamentally from black hole event horizons. Black hole event horizons are surfaces in space-time once crossed. Escape is impossible because all future-directed paths lead to the singularity. Light emitted inside a black hole horizon cannot escape. Cosmological event horizons are observer-dependent surfaces in space. Different observers have different event horizons centered on themselves. Light emitted beyond an observer's cosmological event horizon doesn't fall into a singularity, but simply never reaches that observer due to expansion. Other observers farther away might receive the light. The horizon is a limit on communication, not a physical surface. The horizon's existence raises philosophical questions. If events beyond the horizon cannot affect us, do they exist meaningfully? Some physicists argue the unobservable universe, everything beyond the particle horizon, is metaphysics rather than physics, irrelevant to science because it's untestable. Others counter that general relativity describes space-time everywhere, not just the observable region, and we have no reason to believe physics stops at observational limits. The equations governing cosmology apply uniformly. The same expansion that affects the observable universe affects the unobservable universe identically. Future observations will see fewer galaxies as some cross the event horizon. Currently, the observable universe contains roughly 2 trillion galaxies. In 150 billion years, most galaxies beyond the local group will have receded beyond the event horizon and faded from view. The local group, Milky Way, Andromeda, Triangulum, and dozens of dwarf galaxies gravitationally bound to us will remain observable because gravitational binding overcomes expansion. But essentially all other galaxies will disappear. Future astronomers in that epoch will see a universe containing only their local group surrounded by darkness, with no evidence of the larger cosmos. The cosmic microwave background will also fade and redshift beyond detection. Currently, at 2.7 Kelvin, the CMB temperature decreases inversely with the scale factor. In 50 billion years, temperature will be 1 Kelvin. In 500 billion years, 0.1 Kelvin. As temperature drops, detecting the CMB becomes progressively harder, eventually requiring impractically large antennas and integration times. By the time temperature reaches 10 millikelvin in 27 trillion years, detection would require antenna size comparable to planetary orbits, making observation effectively impossible. The CMB will still exist, filling space with radiation, but it will be undetectable, removing key evidence for the Big Bang. The event horizon's presence means the universe has finite information content from any observer's perspective. Information can only travel at light speed, so information from beyond the event horizon can never reach us. The maximum information accessible to us equals the entropy within the event horizon, which scales as the horizon's area divided by 4 times Newton's gravitational constant. For cosmological event horizon at 16 billion light-years, this gives roughly 10 to the 123rd bits, enormous but finite. This suggests holography, all physics within a volume, might be encoded on its boundary, applies to cosmology, not just black holes. The horizon's existence is observationally testable in principle. If we could observe galaxies near the event horizon and measure their apparent recession velocity, we'd find velocities approaching or exceeding light speed. But in practice, such galaxies are so distant redshift above 2 or 3 that measuring proper motions is impossible with current technology. Their transverse velocities across the sky are tiny milliarcoseconds per century, far below measurement precision. We infer the event horizon from cosmological models constrained by observations of expansion history, not from direct observation of galaxies at the horizon. The horizon will ultimately dominate the observable universe's future. While the particle horizon defining what we can see slowly expands as more time passes for light to travel, the event horizon shrinks, limiting what we can interact with. Asymptotically, the event horizon approaches the Hubble radius c over h infinity, stabilizing at about 5.3 billion light-years. This will be the ultimate size of our causal patch, the region we can influence, and that can influence us. Everything beyond will be as inaccessible as regions beyond light cones in special relativity, separated not by prohibition on faster-than-light travel, but by expansion that outpaces light itself. The infinite possibilities from eternal inflation. Eternal inflation, proposed by Andrei Linde in 1983 and developed by Linde Alexander Vilenkin and others, suggests that inflation is an ongoing process occurring forever in some regions while ending in others. In eternal inflation, quantum fluctuations in the inflaton field cause some regions to continue inflating even as other regions stop. Regions that stop inflating undergo reheating. The inflaton field's energy converts to particles, initiating a hot Big Bang like the one we observe. But regions continuing to inflate expand exponentially, vastly exceeding regions that stopped, ensuring inflation never ends globally, even though it ends locally in many places. The process creates a fractal structure. Imagine a region undergoing inflation. Quantum fluctuations cause the inflaton field to vary across space. Some locations have higher field values, others lower. Locations where the field reaches the potential minimum stop inflating and reheat, becoming pocket universes with hot Big Bang initial conditions. Locations where the field remains high continue inflating. These inflating regions themselves have quantum fluctuations, creating new pockets that stop inflating while other parts continue. The process repeats indefinitely, eternal inflation spawning endless pocket universes within an ever-expanding inflating background. Each pocket universe can have different properties depending on how the inflaton field decays and what vacuum state the fields settle into. String theory predicts a vast landscape of possible vacuum states, perhaps 10 to the 500th power different vacua, each with different values for fundamental constants like particle masses, coupling strengths, and cosmological constant. When a pocket forms, it settles into one vacuum chosen randomly by quantum fluctuations. Different pockets have different physics. Some might have cosmological constants too large, preventing galaxy formation. Others might have weak nuclear forces, preventing star formation. Our pocket has properties allowing complexity and observers. The total volume undergoing eternal inflation grows exponentially forever. If inflation expands volume by factor E per Hubble time, and pockets form at some rate per Hubble volume, the inflating volume still dominates. Simple calculation? Start with 1 Hubble volume inflating. After 1 Hubble time, it expands to E Hubble volumes. If one pocket forms stopping inflation in 1 Hubble volume, E-1 Hubble volumes remain inflating. After another Hubble time, these E-1 volumes expand to E times E-1 volumes, while roughly E-1 new pockets form, leaving roughly E times E-1 minus E-1 volumes inflating. For E greater than 1, the inflating volume grows exponentially despite pocket formation. The pocket universes are causally disconnected. Light from one pocket cannot reach another. Each pocket undergoes its own Big Bang, expanding from small size to large. But the pockets are embedded in the exponentially expanding, inflating space, separating them. This inflating space expands faster than light, preventing signals from crossing between pockets. An observer in one pocket sees only their own pocket universe, the observable universe, unaware of other pockets. The pockets are real occupying space-time, containing matter and energy, but observationally invisible to each other. The multiverse, the collection of all pocket universes, is infinite in extent if inflation lasts forever. Eternal inflation naturally produces infinite space containing infinite pockets with every possible configuration. The distribution of pocket properties depends on probabilities for different vacuum states and inflaton trajectories. If some vacuum state has high probability, many pockets settle there. If our vacuum has low probability, few pockets resemble ours, Anthropic reasoning suggests we observe a universe compatible with observers, not necessarily the most probable vacuum, but one from the subset allowing complexity. The measure problem plagues eternal inflation. In an infinite multiverse, every possible event occurs infinitely many times. Comparing infinities is ambiguous. How do we count outcomes to calculate probabilities? Do we weight by volume, by number of observers? Different measures, prescriptions for comparing infinities, give different predictions, undermining the theory's predictive power. The Youngness paradox illustrates the problem. Simple volume measures predict most observers exist in young universes shortly after the Big Bang, when observer density is highest, contradicting our observation of being in a mature universe. Possible resolutions include the causal diamond measure proposed by Bousseau and others, which counts only observers within a single causal diamond, the overlap of past and future light cones of a single event. This makes the measure finite, avoiding infinity comparisons. Another approach is the scale factor time measure, which weighs volumes by their local time coordinate. These measures give different predictions that might be testable. For example, different predictions for cosmological constants value or probability of observing certain CMB features, but none has achieved consensus as the correct measure. String theory's landscape provides a microphysical realization of eternal inflation. String theory, attempting to unify quantum mechanics and gravity, predicts extra spatial dimensions beyond the three we observe. These extra dimensions can curl up in many ways, different compactifications, each corresponding to different vacuum states with different particle physics. The landscape includes perhaps 10 to the 500th vacua. During eternal inflation, pockets explore this landscape, settling into different vacua. Our pocket settled into a vacuum with specific values for constants, allowing atoms, chemistry, stars, planets, and life. Anthropic selection becomes inevitable in eternal inflation with landscape. If the multiverse contains pockets with all possible physics, only some allow observers. We necessarily observe ourselves in a pocket compatible with our existence anthropic principle. This seems circular, explaining properties by assuming observers exist to observe them, but it has predictive power. If multiple vacua allow observers but with different cosmological constants, we should observe a value neither extremely small nor extremely large, but typical among observer-compatible vacua. Calculations suggest the observed dark energy density is roughly typical, not the most probable, but within the expected range. Eternal inflation is not universally accepted. Some physicists argue its unfalsifiable predictions require solving the measure problem, which may be impossible. Others note that eternal inflation is generic. Most inflation models naturally become eternal through quantum fluctuations, making it hard to avoid if inflation occurred at all. The theory explains the cosmological constant's value through anthropic reasoning, which some accept and others reject as scientifically unsatisfying. Testing eternal inflation directly is impossible. Other pockets are beyond observation, but indirect tests through CMB anomalies or cosmological parameter distributions might someday provide evidence. The implications are staggering. If eternal inflation is correct, the universe is infinitely large, containing infinitely many pockets with every possible configuration. Somewhere, infinitely many times, exists an exact copy of you reading this sentence. Somewhere exists a pocket with different physics where atoms can't form. Somewhere exists a pocket where gravity is stronger, preventing structure formation. The observable universe is one pocket among infinity, with properties determined partially by physics and partially by anthropic selection. We live in a vast multiverse where everything that can happen does happen infinitely many times. the connection to the observable universe's size. Eternal inflation guarantees the total universe vastly exceeds observable limits. Even a single pocket universe extends far beyond its local observable region, at least 250 times observable radius from flatness constraints, possibly infinite if the pocket is infinite. But eternal inflation adds another layer, infinitely many pockets, each potentially infinite, embedded in eternally inflating space, expanding faster than light. The total extent is not merely vast, but actually infinite. The observable universe represents one infinitesimal patch of one pocket in an infinite multiverse. We truly live on a tiny island in an endless cosmos, the Planck satellite mapping the universe's baby picture. The Planck satellite, launched by the European Space Agency on the 14th of May 2009, provided the most detailed map of the cosmic microwave background ever created. Operating from the second Lagrange point L2, located 5 million kilometers from Earth, opposite the Sun, Planck observed the entire sky at 9 frequencies, from 30 to 857 GHz, with angular resolution reaching 5 arc-minutes at the highest frequencies. The satellite operated until October 2013, when its helium coolant was exhausted, producing maps that revealed temperature fluctuations of the CMB with precision better than 1 microkelvin. These maps transformed cosmology into a precision science with parameters measured to percent-level accuracy or better. Planck carried 2 instruments: the low-frequency instrument, or LFI, operating at 30, 44, and 70 GHz, and the high-frequency instrument, or HFI, operating at 100, 143, 217, 353, 545, and 857 GHz. The LFI used radio receivers cooled to 20 Kelvin by passive radiators. The HFI used bolometers, sensitive thermometers, detecting temperature changes from absorbed photons cooled to 0.1 Kelvin by a dilution refrigerator, the coldest place in space. The multi-frequency observations allowed separation of CMB signals from foreground contamination, including galactic dust emission, synchrotron radiation from relativistic electrons spiraling in magnetic fields, and free emission from ionized gas. The Planck mission released data in 3 stages. Preliminary results in 2011 based on 15.5 months of observations. The first cosmological results in March 2013 based on the full mission data, and final results in 2018, including improved analysis and polarization measurements. The 2013 release caused excitement and revision of cosmological parameters. The universe's age increased from 13.75 billion years, measured by WMAP, to 13.82 billion years. The Hubble constant decreased from 71 to 67.4 kilometers per second per megaparsec. Dark energy's fraction decreased slightly from 72% to 68%. These changes, while small, represented the most precise determinations available and became the standard values cited in cosmology papers. The 2018 final release refined parameters further and provided full sky polarization maps. The age settled at 13.797 plus or minus 0.023 billion years, uncertainty only 0.17%. The Hubble constant remained 67.4 plus or minus 0.5 kilometers per second per megaparsec, uncertainty 0.7%. Total density parameter omega total equaled 1.0001 plus or minus 0.0018. confirming flatness to 0.2%. Dark energy fraction omega lambda equaled 0.684 plus or minus 0.00. 7 uncertainty 1%. Dark matter fraction omega dark matter equaled 0.265 plus or minus 0.004, uncertainty 1.5%. These uncertainties represented factors of 2 to 10 improvement over WMAP. Planck's temperature map shows the CMB with exquisite detail. The average temperature is 2.7255 Kelvin uniform to 1 part in 30,000 across the sky. Superimposed on this uniformity are fluctuations, hot and cold spots with amplitude about 100 microkelvins. These fluctuations have characteristic angular scales determined by physics at recombination. The largest scales, tens of degrees, reflect fluctuations that hadn't had time to oscillate before recombination, preserving primordial density variations. Medium scales around 1 degree reflect the sound horizon scale where acoustic oscillations reached maximum amplitude. Small scales arc minutes show damping as photon diffusion smoothed fluctuations below certain sizes. The power spectrum, statistical distribution of fluctuation amplitudes versus angular scale, contains the cosmological information. The power spectrum shows peaks at specific angular scales corresponding to harmonics of the sound horizon. The first peak at multipole moment, approximately 220 angular scale, 0.8 degrees, corresponds to regions that compressed by gravity exactly once before recombination. The second peak, at approximately 540, corresponds to regions that compressed and re-expanded. The third peak, at approximately 800, corresponds to 2 compressions. Peak heights and positions depend on densities of baryons, dark matter, dark energy, and radiation, allowing simultaneous measurement of all components from a single dataset. Polarization measurements added another dimension. CMB photons are about 5% polarized. Their electric fields oscillate preferentially in certain directions rather than randomly. This polarization arises from scattering. At last, scattering photons scatter off electrons, acquiring linear polarization perpendicular to the scattering plane. The polarization pattern across the sky encodes additional information about velocity flows at recombination and potentially about gravitational waves from inflation. Planck measured E-mode polarization curl-free patterns, analogous to electric fields across the full sky, confirming predictions and improving parameter constraints. B-mode polarization curl patterns from gravitational waves remained undetected, though Planck set upper limits. The Planck data revealed unexpected anomalies, features in the CMB that don't match lambda CDM predictions. The CMB shows slightly less power at large angular scales, above 5 degrees, than predicted, a feature called the low anomaly. There's an asymmetry between the northern and southern hemispheres. One hemisphere has slightly higher fluctuation amplitude. A large cold spot, a region 10 degrees across, with temperature 70 microkelvins below average, appears in the southern hemisphere, colder than expected from statistical fluctuations. These anomalies are marginally significant, around 2 to 3 sigma, making their interpretation uncertain. They might be statistical flukes, or systematic errors, or hints of new physics beyond lambda CDM. The cold spot generated particular interest and speculation. One proposal suggested it results from a supervoid, an unusually large, underdense region along the line of sight that imprints temperature decrement through the integrated Sachs-Wolf effect. Surveys found a supervoid at appropriate distance, but calculations showed it couldn't fully explain the cold spot's temperature. Another proposal suggested the spot reflects a collision between our bubble universe and another bubble during inflation. The collision would create a temperature decrement at the collision point, but detailed analysis showed collision signatures wouldn't match observations. The cold spot remains unexplained, likely a statistical fluctuation, but possibly something more interesting. Planck's scientific legacy extends beyond parameter measurements. The mission validated inflation theory by confirming its prediction of nearly scale-invariant density perturbations, the spectral index n sub s equals 0, 9,649 plus or minus 0.0042, close to, but distinctly less than, the scale-invariant value 1. This rules out alternatives, like topological defects, that predict different spectral indices. Planck constrained the sum of neutrino masses to less than 0.12 electron volts, much tighter than laboratory experiments achieve. The mission measured the effective number of light particle species as 2.99 plus or minus 0.17, consistent with exactly 3 neutrino species, and ruling out additional light particles that would affect expansion rate at recombination. The satellite's name honors Max Planck, the German physicist who founded quantum theory. In 1900, Planck solved the ultraviolet catastrophe, the failure of classical physics to explain blackbody radiation spectra, by proposing that energy is quantized in units of h times frequency, where h is Planck's constant. The CMB is a blackbody spectrum, making the name doubly appropriate. The mission continued ESA's tradition of naming spacecraft after famous scientists, following satellites like Herschel, named for William Herschel, who discovered infrared radiation, and Hipparchus, named for the ancient Greek astronomer Hipparchus. Planck's data remain the gold standard for CMB observations. While future experiments will improve certain measurements, particularly polarization and small-scale power spectrum, Planck's full-sky temperature map at arc-minute resolution will remain unmatched for decades. Ground-based experiments like the Atacama Cosmology Telescope and South Pole Telescope achieve higher resolution but cover only portions of the sky. Planned space missions like Japan's Lightbird focus on polarization rather than temperature. Planck's combination of full sky coverage, multi-frequency observations, and temperature sensitivity represents a singular achievement unlikely to be surpassed until a next-generation CMB space mission flies perhaps in the 2040 seconds or 2050 seconds. The Planck 2018 results highlighted the Hubble tension, the discrepancy between CMB-derived Hubble constant at 67.4 km per second per megaparsec and local measurements at 73 km per second per megaparsec. This tension has intensified as both measurements improved. Planck's precise determination makes the tension more significant. Either systematic errors exist in local measurements or new physics beyond lambda CDM is required. Proposed resolutions include early dark energy, varying dark energy equation of state, sterile neutrinos, or modifications to dark matter interactions. Future observations will test these possibilities, potentially requiring the first major revision to the standard cosmological model in decades. The baryon acoustic oscillations measuring cosmic scale. Baryon acoustic oscillations, or BAO, are remnants of sound waves that propagated through the early universe's plasma before recombination. These waves were pressure oscillations, compressions, and rarefactions, driven by gravitational collapse fighting against photon pressure. The oscillations began from quantum fluctuations during inflation and grew until recombination at 380,000 years, when electrons and protons combined into atoms, eliminating free electrons and ending photon pressure. At this moment, the oscillations froze, imprinted into the matter distribution at a characteristic scale equal to the sound horizon, approximately 490,000 light-years at recombination, or 490 million light-years today, after accounting for expansion. The BAO scale serves as a standard ruler, a known physical size that appears as different angular scales or redshift separations depending on distance and geometry. Just as holding a ruler at arm's length subtends a larger angle than at 10 meters, the BAO scale subtends different angles at different redshifts. By measuring the angular size or redshift space size of the bow feature in galaxy surveys, astronomers determine cosmological distances and expansion rates at various epochs. This provides independent checks on supernova measurements and CMB-derived parameters, breaking degeneracies and improving overall constraints on dark energy and other cosmological components. The sound horizon at recombination can be calculated precisely. Sound waves in the photon-baryon plasma propagated at speed to c divided by the square root of 3, where c is light speed. The factor of square root of 3 comes from the plasma's equation of state. Integrating this speed over time from the Big Bang to recombination gives the distance sound travelled, approximately 147 megaparsecs in comoving coordinates, or 480,000 light-years in physical distance at recombination. After the universe expanded by factor 1091 from recombination to present, this scale stretched to 147 megaparsecs, or 480 million light-years, the distance between galaxy overdensities created by the frozen sound waves. Detecting BAO requires surveying millions of galaxies to map the large-scale structure. The first detection came in 2005 from 2 independent teams analyzing data from the Sloan Digital Sky Survey, or SDSS. The 2DF Galaxy Redshift Survey also contributed early measurements. These surveys measured redshifts for hundreds of thousands of galaxies, revealing their 3-dimensional positions. Statistical analysis of galaxy separations showed a subtle excess of galaxy pairs, separated by about 490 million light-years compared to random distribution, the BAO bump. The bump appears as a single feature in the galaxy correlation function at 150 megaparsec separation, exactly matching predictions from CMB observations of the sound horizon. The SDSS-3 Baryon Oscillation Spectroscopic Survey, or BOSS, operated from 2009 to 2014 and dramatically improved BAO measurements. BOSS observed 1.5 million galaxies across 1/4 of the sky, measuring redshifts with precision better than 100 kilometers per second. The survey mapped galaxies at redshifts 0.2 to 0.7, corresponding to look-back times 2.5 to 6.5 billion years, spanning the epoch when dark energy began dominating. BOSS detected the BAO feature with high significance, more than 5 sigma in multiple redshift bins, tracing expansion history over this crucial period when acceleration began. The SDSS-4 Extended Baryon Oscillation Spectroscopic Survey, or EBOS, continued from 2014 to 2020, extending measurements to higher redshifts. EBOS observed 500,000 additional galaxies at redshifts 0.6 to 1, plus 500,000 quasars, extremely luminous galactic nuclei powered by supermassive black holes at redshifts 0.9 to 2.2. The quasar measurements probed the universe when it was only 3 to 6 billion years old, much younger than accessible with galaxy surveys. Combined BOSS and EBOS data provide BAO measurements spanning redshift 0, 2 to 2.2, covering more than 11 billion years of cosmic history. BAO measurements constrain both angular diameter distance and Hubble parameter simultaneously. The angular diameter distance relates an object's physical size to its angular size on the sky. Farther objects appear smaller. The Hubble parameter determines recession velocities for given distances. BAO features appear both as angular separations perpendicular to the line of sight, determined by angular diameter distance, and redshift separations along the line of sight, determined by Hubble parameter. Measuring both separations simultaneously breaks the degeneracy between distance and expansion rate, providing orthogonal constraints that improve overall parameter determination. The Dark Energy Spectroscopic Instrument, or DESI, began operations in 2021 on the Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. DESI simultaneously observes 5,000 objects using robotic fiber positioners that move optical fibers to point at selected targets across the telescope's 3-degree field of view. Over 5 years, DESI will measure 40 million galaxy and quasar redshifts, 30 times more than BOSS, mapping the universe's structure from redshift 0.1 to 3.5. DESI's first-year data, released in 2024, already improved BAO measurements, detecting the feature at redshift 0.5 with unprecedented precision and revealing hints that dark energy might not be perfectly constant. The first-year DESI results suggested possible time variation in dark energy's equation of state W might not equal exactly -1, but could vary with redshift. The data preferred models where W was less negative in the past, around -0.7, at redshift 2 becoming more negative recently and approaching -1 today. This would mean dark energy's density increased faster than constant vacuum energy would predict, causing more rapid acceleration recently. But the preference was marginal, around 2.5 sigma, insufficient to claim discovery. Future DESI data and other surveys will test whether this hint strengthens or disappears. BAO measurements provide crucial checks on CMB results. The CMB measures expansion history primarily at high redshift, the sound horizon at Z equals 1090, plus some information from the integrated Sachs-Wolf effect at intermediate redshifts. Supernovae probe Z less than 2, primarily recent epochs. BAO fills the gap, measuring expansion at redshifts 0.2 to 3, where neither CMB nor supernovae dominate. The consistency of BAO measurements with CMB predictions validates the lambda CDM model across cosmic history. Any inconsistency would signal new physics, making BAO surveys frontline searches for deviations from the standard model. Future BAO surveys will improve measurements further. The Euclid mission, launched in 2023, will measure spectroscopic redshifts for 50 million galaxies over 1/3 of the sky, providing BAO measurements from Z equals 0.9 to 1.8 with exquisite precision. NASA's Nancy Grace Roman Space Telescope, launching in 2027, will survey 50 million galaxies spectroscopically, measuring BAO from space with stable instruments unaffected by atmospheric distortions. Ground-based projects like DESI and future surveys on the Vera Sea, Rubin Observatory will continue improving measurements from the ground. Combined, these missions will measure the BAO scale to sub-percent precision across cosmic history. The BAO technique has limitations. At high redshift beyond Z, approximately 3, galaxies become faint and rare, making surveys difficult and expensive. Quasars extend to higher redshift, but are sparse only about 100 per square degree at Z greater than 2, compared to 1,000 galaxies per square degree at Z less than 1. The Lyman alpha forest absorption lines from intergalactic hydrogen clouds provides an alternative, allowing BAO measurements from quasar spectra at Z equals 2 to 4. But Lyman alpha analyses are complex, requiring careful modelling of astrophysical effects that can mimic or distort the BAO signal. Despite limitations, BAO remains among the most powerful cosmological probes. The discovery and measurement of BAO represents a triumph of precision cosmology. The acoustic oscillations predicted decades ago, visible in the CMB as temperature fluctuations, reappear in galaxy distributions at low redshift as a subtle 1 to 2% enhancement in clustering at 150 megaparsec scale. Detecting this feature required surveys of millions of galaxies with precise redshifts and sophisticated statistical analyses. The success validates theoretical understanding of structure formation and provides a standard ruler independent of CMB or supernovae, anchoring our knowledge of cosmic expansion history and the properties of dark energy driving acceleration. The large-scale structure spanning billions of light-years. The universe's large-scale structure, the distribution of galaxies, clusters, and voids across cosmic scales, reveals patterns extending billions of light-years. Galaxies aren't distributed randomly, but cluster along filaments and sheets surrounding vast empty voids, creating a cosmic web resembling soap bubbles or neural networks. The largest structures include the Sloan Great Wall at 1.37 billion light-years length, the Boss Great Wall at roughly 1 billion light-years, and the Hercules Corona Borealis Great Wall at approximately 10 billion light-years, though the reality of structures this enormous remains debated. These structures trace the universe's matter distribution, revealing how initial density fluctuations grew through gravitational collapse over billions of years. The cosmic web consists of 4 elements: clusters, filaments, sheets, and voids. Clusters are dense concentrations where hundreds to thousands of galaxies collect. The Coma cluster contains about 1,000 galaxies in a region 20 million light-years across. Filaments are elongated structures where galaxies line up along thin threads spanning tens to hundreds of millions of light-years. Sheets or walls are two-dimensional surfaces where galaxies cluster. The CFA, 2 Great Wall, discovered in 1989, extends 500 million light-years across, but is only 15 million light-years thick. Voids are nearly empty regions between structures containing few or no galaxies, with diameters reaching hundreds of millions of light-years. The Sloan Great Wall, discovered in 2003 by J. Richard Gott and Mario Jurich from Sloan Digital Sky Survey data, stretches 1.37 billion light-years from end to end. The structure lies at average redshift Z, approximately 0.073, corresponding to distance about 1 billion light-years. It's not a continuous solid wall, but a connected network of galaxy clusters and filaments forming a coherent structure. The wall includes the Corona Borealis supercluster and other rich clusters. At 1.37 billion light-years, the structure subtends about 60 degrees on the sky, occupying a substantial fraction of the observable universe as seen from Earth. The Hercules Corona Borealis Great Wall, claimed as the largest structure in the universe, was identified in 2013 by Istvan Horvath and colleagues by analysing gamma-ray burst distributions. Gamma-ray bursts trace massive star formation and thus galaxy concentrations. The structure extends roughly 10 billion light-years across at average redshift Z, approximately 2, corresponding to distance about 10 billion light-years look-back time, when the universe was only 3.8 billion years old. However, the structure's reality is controversial. Statistical tests show only marginal significance, and the gamma-ray burst distribution might result from chance clustering rather than a physical structure. Many cosmologists remain skeptical of claims for structures exceeding several billion light-years. The theoretical maximum structure size is roughly the horizon scale at the epoch when the structure formed. Structures grow through gravitational instability, which requires time. A structure 10 billion light-years across would need most of cosmic history to assemble. But in the standard lambda CDM model, structures above approximately 1 billion light-years are difficult to form because there hasn't been enough time for gravity to pull matter together over such distances, and cosmic acceleration in recent epochs further inhibits growth. Structures beyond 1.2 billion light-years challenge the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. The cosmological principle states that on sufficiently large scales, above about 300 million light-years, the universe should appear uniform. Galaxy surveys confirm this. At scales below 100 million light-years, clustering is strong with fractal-like structure. Above 300 million light-years, the distribution becomes increasingly uniform. Above 1 billion light-years, variations in matter density drop below 10%. If structures as large as 10 billion light-years truly exist, they violate the cosmological principle's scale assumption, potentially requiring revision of the standard model. Most cosmologists favor explanations where apparent megastructures are chance alignments rather than gravitationally bound systems. Voids represent the universe's dominant volume. The Boötes void, discovered in 1981 by Robert Kirshner and colleagues, spans 330 million light-years in diameter and contains only about 60 galaxies, far fewer than the thousands expected in a typical region that size. The void appears nearly empty from outside, but the few galaxies inside are distributed along thin filaments rather than uniformly. The void formed as matter drained into surrounding overdensities, leaving underdense regions that expanded faster than the cosmic average. Voids comprise about 80% of the universe's volume, but contain less than 10% of its galaxies. The largest known void is the CMB cold spot supervoid, identified in 2015 by Istvan Shahpoudi and colleagues. This void spans about 1.8 billion light-years in diameter, centered at redshift Z, approximately 0.22, corresponding to distance 2.5 billion light-years. The supervoid underlies the cold spot in the CMB, a region 10 degrees across with temperature 70 microkelvins below average. Photons crossing the void experience the integrated Sachs-Wolf effect. They fall into the void's gravitational potential, gaining energy, then climb out, losing energy. But because the universe expands during transit and dark energy causes acceleration, the void's potential becomes shallower. Photons don't climb as high exiting as they fell entering, producing net energy loss and appearing as cold spot. Structure growth stopped when dark energy began dominating around redshift Z approximately 0.56 billion years ago. Before this epoch, during matter domination, density perturbations grew proportionally to the scale factor. Doubling the universe's size doubled the density contrast. Galaxies and clusters formed during this period through hierarchical merging. Small structures merged into larger ones. But as dark energy took over, expansion accelerated and growth slowed. Density contrasts now increase logarithmically rather than linearly. Future growth will cease entirely. Structures that haven't collapsed by now will remain frozen as accelerating expansion prevents further collapse beyond the local group scale. Redshift space distortions provide another probe of large-scale structure and cosmic growth. Galaxies have peculiar velocities, random motions relative to the Hubble flow, typically a few hundred kilometers per second, caused by gravitational attraction toward nearby overdensities. These velocities add to recession velocities, distorting redshift measurements and making structures appear stretched or compressed along the line of sight. The distortion pattern depends on the growth rate of structure, which depends on matter density and dark energy properties. Measuring redshift space distortions tests whether structures grow at the rate predicted by general relativity or require modifications. The Millennium simulation, completed in 2005 by the Virgo Consortium, modeled structure formation by simulating 10 billion dark matter particles in a cubic volume 2.2 billion light-years on a side. The simulation followed structure evolution from redshift Z equals 127, when the universe was 100 million years old, to the present. Results showed how tiny initial density variations, 1 part in 100,000, grew into the cosmic web through purely gravitational dynamics. The simulation reproduced observed galaxy clustering statistics, cluster abundance, and filament properties, confirming that cold dark matter with lambda CDM parameters explains large-scale structure. Subsequent simulations with better resolution and larger volumes have refined predictions further. The cosmic web's topology, its connectivity, and geometry provides cosmological constraints. The web's filamentary structure reflects the nature of gravitational collapse in 3 dimensions. In 1D, collapse forms sheets, in 2D forms filaments, in 3D forms nodes, clusters connected by filaments with sheets between, at surrounding voids. The observed topology matches cold dark matter predictions. Alternative scenarios like warm dark matter, where dark matter particles have higher velocities, would erase small-scale structure, producing fewer filaments and changing topology. The observed intricate web, with structure down to megaparsec scales, supports cold dark matter. Future surveys will map structure with unprecedented detail. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, beginning in 2025, will photograph the entire southern sky every few nights for 10 years, detecting billions of galaxies and measuring their positions, shapes, and colors. Weak gravitational lensing, subtle distortions of galaxy shapes by intervening matter will map dark matter distribution directly. The Euclid mission and Nancy Grace Roman Space Telescope will measure redshifts for tens of millions of galaxies, creating 3-dimensional maps revealing structure evolution. Combined, these missions will test lambda CDM at percent-level precision, potentially revealing discrepancies requiring new physics. The multiverse theories beyond our cosmos. The multiverse, the concept that our universe is one among many, exists in multiple theoretical frameworks with different levels of speculation and testability. Physicist Max Tegmark classified multiverse theories into 4 levels in a 2003 paper, ranging from the relatively conservative level 1 to the highly speculative level 4. Level I consists of regions beyond our observable universe in an infinite space with the same physical laws. Level 2 comprises bubble universes from eternal inflation with potentially different physical laws. Level 3 involves quantum many worlds, where every quantum measurement spawns parallel branches. Level 4 suggests all mathematically consistent structures exist as physical realities. Each level makes increasingly bold claims about unobservable realms. Level I multiverse, the simplest version, assumes space extends infinitely beyond the observable universe and is filled with matter distributed according to the same statistical properties we observe. If space is infinite and matter distribution is ergodic, all possible configurations occur somewhere, then every possible arrangement of particles exists infinitely many times. An exact copy of you exists in infinitely many locations, infinitely far away. This follows from simple probability. If you flip a coin infinitely many times, every finite sequence appears infinitely often. Similarly, if space is infinite, every finite volume configuration appears infinitely often, including exact copies of Earth, the solar system, and the observable universe. The distance to the nearest identical copy can be estimated. The observable universe contains roughly 10 to the 90th particles. The number of possible configurations is vastly larger, but finite for any finite volume, roughly 10 to the 10 to the 120th, depending on assumptions about quantum states. If space is infinite and uniformly filled, an identical region should exist at distance roughly 10 to the 10 to the 120th Hubble radii, incomprehensibly far but finite. This assumes uniform distribution. Clustering makes identical copies closer but still impossibly distant. The level I multiverse requires only infinite space, not new physics, making it the most conservative multiverse proposal. Level 2 multiverse arises from eternal inflation. As discussed in Chapter 14, eternal inflation creates infinitely many bubble universes within an ever-expanding inflating background. Each bubble forms when inflation ends locally, reheating to create a hot Big Bang. The bubbles are causally disconnected. Light from one bubble cannot reach another due to the exponentially expanding space between them. Each bubble can have different properties depending on which vacuum state the fields settle into during reheating. String theory's landscape, with 10 to the 500th possible vacua, provides a microphysical realization, giving each bubble potentially different particle physics. Different bubbles in Level 2 multiverse could have different fundamental constants. The electron's mass, the strength of electromagnetic force, the cosmological constant, and other parameters we consider fundamental might vary between bubbles, determined by which vacuum each bubble settled into. Most vacua likely produce universes hostile to life, cosmological constants too large, preventing galaxy formation, weak nuclear forces too weak for fusion in stars, or forces with wrong strengths preventing chemistry. The observable universe's properties might reflect anthropic selection. We observe a life-compatible universe because only such universes contain observers. This is controversial. Some accept anthropic reasoning as scientific, others reject it as unfalsifiable. Level 3 multiverse, the many worlds interpretation of quantum mechanics, proposes that every quantum measurement causes the universe to split into multiple branches, each representing different measurement outcomes. When a photon hits a half-silvered mirror and could reflect or transmit, the universe splits into two branches, one where it reflected, another where it transmitted. These branches are real, occupying Hilbert space, the mathematical space of quantum states, but not physical space. They're parallel realities that cannot interact or communicate. Every quantum event, and there are countless per second, spawns uncountably many branches, creating an ever-growing tree of universes. The many worlds interpretation was proposed by Hugh Everett in 1957 as a solution to the quantum measurement problem. Standard Copenhagen interpretation says quantum systems exist in superposition simultaneously in multiple states until measured, whereupon they collapse to a single state. But what causes collapse? Observation by a conscious mind seems mystical. Many worlds avoids collapse. Systems remain in superposition, but the observer becomes entangled, also entering superposition of having seen different outcomes. Each branch of the superposition corresponds to a world. There's no collapse, only branching. All outcomes occur, each in separate worlds. Many worlds remains controversial despite widespread use. Critics argue it's extravagant, postulating uncountably infinite, unobservable branches to avoid collapse seems anti-parsimonious. Proponents counter that many worlds is actually simpler. It takes quantum mechanics equations literally without adding collapse mechanisms. The interpretation makes the same experimental predictions as Copenhagen for observations within a single branch, making it empirically equivalent. Preference depends on philosophical views about ontology, what exists, and parsimony, whether simplicity means simpler mathematics or fewer postulated entities. Level 4 multiverse is the most speculative. All mathematical structures exist as physical realities. This mathematical universe hypothesis, proposed by Max Tegmark, suggests that if a mathematical structure can be defined consistently, a set of axioms producing a self-consistent theory, then a corresponding physical universe exists. Our universe corresponds to some mathematical structure, perhaps described by string theory or another fundamental theory. But infinitely many other mathematical structures exist, each corresponding to a universe with radically different laws of physics. Some structures might not have space, time, particles, or causality as we understand them. The Level 4 proposal follows from assuming the universe is purely mathematical, the external reality hypothesis, and that all mathematical structures are equally real. If physical reality is mathematical, and there's no reason to privilege one structure over others, all structures should exist. This seems wildly speculative, but has an internal logic. Critics argue that not all mathematical structures can be physical. Many are inconsistent or lack the complexity to support observers. Proponents counter that we'd only observe ourselves in structures complex enough for observers, explaining why our universe seems special despite all structures existing. Multiverse theories face the fundamental problem of testability. By definition, other universes in a multiverse are beyond observation. We can't detect other inflating bubbles, parallel quantum branches, or level 4 structures. Science requires testability, but multiverses seem untestable. Proponents argue that multiverse theories make indirect predictions. Eternal inflation predicts bubble collisions might leave imprints on the CMB. Many worlds makes no predictions different from Copenhagen, but simplifies foundations. Level 2 multiverse with anthropic reasoning predicts our universe's properties should be typical among observer-compatible universes testable through cosmological constant measurements or other parameter distributions. Detecting evidence for a multiverse would require extraordinary observations. Bubble collisions from eternal inflation would appear as circular temperature patterns in the CMB cold spots where our bubble collided with another. Searches have found no definitive signals, though the CMB cold spot remains unexplained. Quantum branching in many worlds might produce subtle decoherent signatures if branches couple weakly rather than completely decoupling. Level IV mathematical structures might show up as inconsistencies in fundamental theory. Our universe might be approximated by multiple mathematical structures that join at some scale. All these possibilities remain speculative and have produced no convincing evidence. The philosophical implications are profound. If Level 1 multiverse exists, everything possible happens somewhere. Every choice you could make is made by some copy in another region. If Level 2 exists, physical laws are environmental, not fundamental, but accidents of which vacuum formed during inflation. If Level 3 exists, personal identity becomes ambiguous. Many versions of you exist in different branches, all equally real. If Level 4 exists, reality is purely mathematical. Physical existence is just certain mathematical structures. These implications challenge intuitions about uniqueness, laws, identity, and reality. Critics argue multiverse theories aren't science, but metaphysics, philosophical speculation beyond empirical investigation. Defending theories by invoking infinite, unobservable entities violates Occam's razor and scientific methodology. Proponents counter that multiverses arise naturally from successful theories, general relativity predicting eternal inflation, quantum mechanics implying many worlds, string theory producing landscape making multiverses consequences rather than assumptions. Whether multiverse theories qualify as science depends on definitions. They're motivated by established physics and make some testable predictions, but the core claims about other universes remain unverifiable. The multiverse concept, whatever its ultimate status, highlights how cosmology pushes scientific boundaries. The observable universe is all we can see, but physical law might extend far beyond, creating realms forever hidden. The true size of reality, whether it's one universe, many universes, or infinite mathematical structures, remains unknown. Our 3 billion light-year observable universe might be an infinitesimal island in a vaster multiverse, or it might be everything that exists. Until new observations or theoretical breakthroughs provide evidence, the question remains open, a frontier where physics meets philosophy and imagination encounters the limits of knowledge. The true size estimates from theory and observation. The universe's true size, its total extent beyond the observable region, remains unknown, but constrained by theory and observation. The minimum size, based on spatial flatness measurements from Planck, is at least 250 times the observable universe's radius, giving diameter at least 23,000 billion light-years, or 23 trillion light-years. This minimum assumes the universe has slight positive curvature, a closed spherical geometry at the limit of detectability. If curvature is negative, open, hyperbolic geometry, or exactly zero flat geometry, the universe extends infinitely. Current observations cannot distinguish these possibilities, leaving the universe's ultimate extent anywhere from 23 trillion light-years to infinite. Inflation theory provides stronger, lower bounds. Even minimal inflation with 60 e-folds, the minimum needed to solve the horizon and flatness problems, expands the universe by factor e to the 60th, approximately 10 to the 26th. If the inflated region was initially at the Planck scale, 10 to the minus 35th meters, it expanded to roughly 10 to the minus 9th meters, or 1 nanometer, at the end of inflation. Subsequent expansion to today increased size by another factor of about 10 to the 28th, giving total extent roughly 10 to the 19th meters, or 1 billion light-years. This is the size of the causally connected region space that was in thermal contact before inflation separated it beyond horizons. But the observable universe is only a small part of this inflated region. The observable universe's radius, 46.5 billion light-years, or 4.4 times 10 to the 26th meters, is much larger than 10 to the 19th meters might suggest, because the observable universe isn't the initially inflated region, but a small patch within it. The entire inflated region would be exponentially larger. If inflation lasted 70 e-folds instead of 60, the region expanded by extra factor e to the 10th, about 22,000. The total inflated region would be 22,000 times larger in each dimension, or 10 to the 13th times larger in volume. The observable universe would comprise 1 part in 10 to the 13th of the inflated region. More extreme inflation models predict vastly larger sizes. Inflation lasting 100 e-folds not implausible, given that eternal inflation suggests some regions inflate much longer, would expand by factor 10 to the 43rd. The total inflated region would span roughly 10 to the 36th light-years, a 1 followed by 36 zeros. The observable universe at 10 to the 11th light-years would be fraction 10 to the minus 25th of the total. Even this understates the true size. If eternal inflation is correct, eternal inflation produces infinite space containing infinitely many inflated regions, each potentially infinite if the underlying space has flat or hyperbolic geometry. The string theory landscape suggests another estimate. With 10 to the 500th possible vacua and eternal inflation producing bubbles that explore this landscape, the multiverse contains regions corresponding to each vacuum. If each vacuum occupies a typical inflated region, say 10 to the 26th times larger than the observable universe in each dimension, the total volume exceeds 10 to the 500th times 10 to the 78th, or 10 to the 578th times the observable volume. This assumes each vacuum appears roughly once. If vacua appear multiple times, as eternal inflation suggests, the total is much larger. These numbers strain comprehension. They're vastly beyond anything measurable or imaginable. The observable fraction can be quantified. If the true universe is 250 times the observable radius to the minimum, from flatness the volume ratio is 250 cubed, or 15.6 million to 1. The observable universe comprises one part in 16 million of the total. If inflation expanded by 10 to the 26th, the volume ratio is 10 to the 78th. To 1 we see one part in 10 to the 78th. If the universe is infinite, the fraction is 0, the observable universe is infinitesimal. Regardless of which case obtains, the observable universe is a tiny fraction of the whole, making nearly all of reality forever hidden beyond our cosmic horizon. The unobservable universe is as real as the observable universe according to general relativity. The same physical laws, Einstein's field equations, quantum mechanics, thermodynamics, apply everywhere. The cosmic microwave background fills all space, not just the observable region. Galaxies form beyond the horizon through the same processes as in the observable universe. Dark matter, dark energy, and matter densities take the same values far beyond what we see. The unobservable universe isn't hypothetical or speculative, but a straightforward consequence of applying successful physical theories uniformly rather than arbitrarily stopping at observational limits. Future observations will tighten constraints but cannot reveal the true size. Improved CMB measurements might determine curvature to 0.01% instead of 0.2%, raising the minimum size from 250 to perhaps 2,500 observable radii. But proving exact flatness requires infinite precision unattainable. If the universe is infinite, we can never prove it. We can only set progressively larger lower bounds on curvature radius. If it's finite but very large, say 1 trillion times observable size, detecting the curvature is impossible with any conceivable experiment. The true size lies beyond direct measurement, knowable only through theoretical inference and model-dependent extrapolation. Philosophical implications abound. The Copernican principle, the idea that we occupy no special place in the cosmos, receives dramatic confirmation. Not only is Earth not the center, and the Sun an ordinary star in an ordinary galaxy, but the observable universe itself is an ordinary patch of a vastly larger whole. We're not special in space or time or observational access. The cosmic humility continues. From Earth as center, to Sun as one star among billions, to Milky Way as one galaxy among trillions, to observable universe as one patch among perhaps infinite patches. Each discovery reveals our place as smaller and less unique. The true size is unknowability, highlights science's limits. Physics describes reality using mathematics and experiment, but vast regions of reality lie forever beyond experiment. We can infer properties using theory. General relativity describes space-time everywhere, not just where we can see, but we cannot verify these inferences observationally. This frustrates some physicists who insist science requires testability. Others accept that theoretical inference from tested principles can yield knowledge about untestable domains. The debate reflects deeper questions about scientific epistemology, what counts as knowledge, and what theories are legitimate. The practical implication: humanity will never explore most of reality. Even at light speed, reaching regions beyond the event horizon at 16 billion light-years is impossible. Expansion carries them away faster than we can approach. Regions beyond the particle horizon at 46.5 billion light-years are currently unobservable and will remain so until their light arrives, if it ever does, given accelerating expansion. Future civilizations billions of years hence will see different observable universes as light from currently unobservable regions arrives, while nearby galaxies recede beyond the shrinking event horizon. But the vast majority of space will remain forever beyond reach real but inaccessible. The universe's true size makes our observable universe, already incomprehensibly large, seem tiny by comparison. The 3 billion light-year diameter, containing 2 trillion galaxies and 10 to the 24th stars, represents perhaps 1 part in 10 to the 78th of an inflated region, which might be one among infinite regions in an eternally inflating multiverse, which might be one structure among infinite mathematical structures if level 4 multiverse is correct. The nested hierarchy of scales, observable universe, within inflated region, within eternal multiverse, within mathematical multiverse, each layer vastly exceeding the previous approaches, the infinite through compounding vastness. Yet, despite this humbling scale, we've measured the observable universe with remarkable precision. We know its age to 0.2%, its geometry to 0.2%, its composition to a few percent. We've mapped its baby picture at 380,000 years old with microkelvin precision. We've traced its expansion history from milliseconds after the Big Bang to the present. We understand how structures formed from quantum fluctuations and grew into galaxies and clusters. This represents an extraordinary achievement from our tiny planet. We've characterized the cosmos across 46.5 billion light-years and 13.8 billion years. That our knowledge extends even to the observable region, let alone hinting at the vaster reality beyond, testifies to human ingenuity and the power of scientific method.